In 2025, Texas is finishing its most ambitious and expensive construction projects ever. From massive highway expansions and energy hubs to futuristic transit systems and tech-driven cities, these megaprojects are set to redefine how the Lone Star State moves and grows. Let's uncover the scale and impact of Texas's megaprojects reaching completion in 2025. Construction of the Texas State Highway 365 Tollway began with extensive site surveying and environmental assessments, given the area's sensitivity to both hydrological patterns and existing urban developments. Civil engineers first conducted geotechnical studies to determine the bearing capacity of the soil, as large portions of the alignment traversed alluvial plains with variable subsoil conditions. These studies inform the design of the subgrade and the depth of excavation required to create a stable foundation for the tollway structure. Once site clearing began, vegetation was removed, utilities were identified and either relocated or protected, and temporary erosion and sediment control measures were installed. Bulldozers, graders, and excavators were deployed in a phased manner to strip the topsoil, cut into embankments, and level the terrain. Given the proximity to flood-prone regions, extensive drainage infrastructure was integrated early in the grading process. This included the installation of reinforced concrete box culverts, precast stormwater inlets, and longitudinal storm sewer systems to manage runoff and prevent roadbed saturation. Next, the base layers were constructed. This began with the application of a geotextile fabric over weak subgrade areas to enhance load distribution. Crushed limestone was brought in and compacted in layers to create a high-density, non-expansive base that would support the weight of the pavement structure and vehicle loads. For quality assurance, nuclear density gauges and Proctor tests were used regularly to verify compaction levels. Concrete paving was selected for most of the tollway due to its longevity and load-bearing capacity. Slip-form pavers were employed to place continuously reinforced concrete pavement. This process involved laying down steel reinforcement, followed by the extrusion of concrete slabs, which were then textured and cured to ensure strength and skid resistance. Joints were carefully sawed at intervals to control cracking, and curing compounds were sprayed to prevent premature moisture loss. Parallel to the mainline construction, interchanges and ramps were built to facilitate connections with existing highways and local roads. These structures required drilled shaft foundations, formed and poured reinforced concrete columns, and precast concrete beams or steel girders, depending on the span and clearance requirements. Falsework and shoring systems were meticulously planned to support these structures during the erection phase, ensuring alignment and stability prior to concrete deck pours. Tolling infrastructure was integrated using overhead gantries equipped with electronic transponders and cameras. These systems were supported by underground conduits for power and fiber optic communication, which were installed prior to paving to avoid later disruption. Intelligent transportation systems, including variable message signs and traffic monitoring sensors, were installed along the corridor to support dynamic tolling and real-time traffic management. Safety features such as guardrails, crash attenuators, and high-mast lighting were implemented throughout the corridor. Landscaping and revegetation of disturbed areas helped control erosion and restored the environmental buffer along the right-of-way. Once construction was substantially complete, final striping, signage, and pavement marking were applied, and punch list items were addressed before the tollway was open to the public. Breaking ground on the VIA Green Line bus rapid transit system required an initial phase of utility mapping and right-of-way coordination through densely developed urban corridors. The alignment followed major arterial roads, necessitating collaboration with city departments and utility companies to relocate existing infrastructure, including water mains, sewer lines, gas pipes, and fiber optic cables. Engineers conducted subsurface utility engineering surveys to precisely map underground features and avoid costly conflicts during construction. After right-of-way clearance, the corridor was milled and excavated in segments to prepare for the installation of the dedicated BRT lanes. Existing asphalt was removed, and the underlying subgrade was reshaped and compacted. Geotechnical stabilization methods were employed where soft soils threatened pavement integrity. These included cement or lime treatment of subgrade layers, especially in areas with expansive clay content common in the region. Base layers were constructed using crushed stone with geogrid reinforcement used at select locations to distribute vehicular loads and reduce differential settlement. Dedicated BRT lanes were then surfaced with high-strength asphalt mixes designed for the repetitive load cycles of rapid transit buses. These lanes were constructed with increased structural depth and improved cross-slope design to enhance drainage and longevity. Curbs and gutters were reformed to accommodate new lane configurations, and bioswales were integrated at strategic locations for stormwater management. Station construction was a major feature of the project. Each BRT station was built with elevated platforms to ensure level boarding, thereby enhancing accessibility and minimizing dwell times. Platforms were constructed using reinforced concrete pads and integrated with steel-framed canopies, which included solar panels for auxiliary power. Electrical conduits were laid beneath the platform surface to support lighting, real-time arrival displays, and fare payment systems. The installation of tactile warning strips and ADA-compliant ramps ensured full accessibility. Signal prioritization infrastructure was installed at major intersections. This involved retrofitting existing traffic signals with transit signal priority controllers that could receive real-time data from approaching BRT vehicles via GPS and cellular communications. Fiber optic backbone was extended along the corridor to provide connectivity for TSP, as well as for security cameras and station monitoring. To support fleet operations, bus-only lanes were demarcated with thermoplastic pavement markings and vertical delineators where necessary. Concrete barriers were used in some high-conflict zones to physically separate BRT traffic from mixed traffic lanes. Special attention was given to designing curbside interface zones at transfer points and park and ride facilities where enhanced pavement, signage, and bus bay geometry were implemented to streamline passenger movement and maintain schedule reliability. As part of the overall system enhancement, centralized control systems were developed at the operations center to monitor vehicle locations, schedule adherence, and station conditions. The system integrated with citywide intelligent transportation systems for comprehensive transit oversight. The final phase of the VIA Green Line BRT project included comprehensive testing of vehicle integration, signal coordination, fare collection systems, and emergency response protocols. Once fully commissioned, the corridor was opened for revenue service, marking a significant step forward in the region's commitment to sustainable, high-capacity urban transit infrastructure. Starting with site selection for the Gigapop Data Center in Red Oak, engineers prioritized proximity to major fiber routes, low seismic risk, and stable ground conditions. Once the parcel was secured, initial development began with topographic surveys and soil borings to evaluate bearing capacity and groundwater levels. Given the data center's critical function, achieving a stable substructure was imperative. Contractors excavated to a depth of several feet, removing organic material and replacing it with engineered fill compacted in lifts. Deep foundation systems, such as drilled piers, were deployed in zones with variable soil strata to ensure long-term structural stability. The facility's footprint was laid out to accommodate modular expansion with a steel-reinforced concrete slab on grade serving as the foundation platform. Reinforcing steel cages were assembled on site and tied into slab pours, using continuous rebar loops to enhance crack resistance and load distribution. After curing, the slab served as the base for pre-engineered structural steel framing. Steel columns and wide flange beams were anchored into embedded base plates and erected using cranes, with lateral bracing and cross members installed to provide rigidity against wind and seismic loads. Envelope construction followed with the installation of insulated metal panels for both thermal performance and security. The roofing system used a mechanically fastened thermoplastic polyolefin membrane over tapered insulation to achieve proper drainage. Roof curbs were pre-installed to support future mechanical units, while penetration points for cabling and ductwork were carefully sealed to maintain the building's energy envelope and meet FM global standards. Critical to the facility's design was its mechanical and electrical infrastructure. Redundant power delivery was achieved using dual utility feeds connected to independent switchgear systems. Below-grade duct banks housed medium voltage cables leading to unit substations, which stepped down voltage for distribution within the facility. Emergency power was backed by multiple diesel generators set on reinforced concrete pads, connected to automatic transfer switches and uninterruptible power supply systems. Each UPS module was installed within a conditioned electrical room, outfitted with fire-rated walls and clean agent fire suppression systems. Cooling was accomplished using a chilled water system with air-cooled chillers mounted on structural steel platforms outside the main building. Inside, computer room air handlers circulated chilled air through raised floor plenums, delivering conditioned air directly to server aisles. Hot aisle containment was implemented to isolate and return warm exhaust air, maximizing cooling efficiency and minimizing energy usage. Cooling system piping was routed through a looped configuration with isolation valves to allow maintenance without service interruption. The data hall itself featured anti-static raised flooring, overhead cable trays for power and fiber distribution, and seismic rated server racks bolted to the slab. Environmental monitoring systems were installed to track temperature, humidity, and particulate levels, all integrated into a building management system with real-time alerts. Security was another major focus, involving perimeter fencing, man-trap entry vestibules, biometric access control, and 24/7 surveillance. All systems were tested through integrated commissioning protocols to validate performance under simulated failure conditions. Once validated, the Gigapop data center in Red Oak went live, offering high availability colocation and cloud services in a purpose-built, mission-critical facility engineered for scalability and resilience. When construction commenced on the X-Energy and Dow small modular reactor nuclear plant in Seadrift, Texas, it marked the integration of advanced nuclear technology within a chemical manufacturing complex. The site selection process prioritized co-location with industrial thermal demand, as the SMR units were designed not only to generate electricity, but also to provide high-temperature steam for Dow's process operations. The initial site preparation involved clearing and grading a large area adjacent to existing infrastructure, with heavy emphasis on creating a stable platform free of differential settlement risks. Soil stabilization was performed using lime treatment, and deep foundation work began with auger cast piles to support critical structures, including reactor containment buildings and turbine halls. The nuclear island construction required a precision-driven sequence of activities. Reinforced concrete foundations were laid for each reactor module, incorporating dense rebar mats and embed plates to support seismic resistance and load transfer. The containment vessel for each SMR unit was fabricated off-site and delivered in modular sections. These modules were lifted into place using heavy lift cranes and positioned within a below-grade reactor cavity formed by cast-in-place concrete with multi-layer waterproofing and radiation shielding components. Each containment structure included integrated penetrations for coolant loop connections, sensor conduits, and control rod drives. Structural liners were welded internally to provide a leak-tight barrier, while the reactor core itself, pre-assembled off-site, was lowered into the containment chamber using precision gantry systems. The high-temperature gas-cooled reactors employed triso fuel particles encased in graphite, requiring specialized fuel handling and containment systems that were installed within the fuel building adjacent to the reactor vault. Above ground, mechanical and electrical auxiliaries were housed in turbine generator halls and heat exchanger enclosures. Power conversion was managed using helium-to-water heat exchangers that fed steam turbines, with the secondary loop connecting to both electrical generators and steam distribution systems used within the Dow chemical complex. To support redundancy and reliability, multiple trains of pumps, valves, and isolation systems were installed with segregated routing to prevent common cause failures. Electrical infrastructure included switchyards and medium voltage transformers tied into the local grid, as well as on-site power distribution to serve critical process loads. Instrumentation and control systems were centralized in a seismically isolated control building, equipped with safety-class digital control systems capable of autonomous reactor shutdown and passive cooling initiation. Fiber optic communication networks linked every module to this control hub for real-time data monitoring and diagnostics. Cooling systems relied on both mechanical draft cooling towers and auxiliary dry cooling radiators, designed to operate under varying ambient conditions while minimizing water withdrawal from nearby sources. Construction crews also installed extensive underground piping networks for the primary and secondary coolant loops, each pressure tested and radiographically inspected to meet nuclear-grade quality assurance standards. To ensure regulatory compliance, all phases of the project were conducted under a rigorous quality assurance framework, with continuous inspection and documentation in accordance with Nuclear Regulatory Commission requirements. Once systems were installed, integrated commissioning followed a phased approach, beginning with cold testing and followed by hot functional testing using non-nuclear heat sources. Only after successful completion of all operational verifications was fuel loading authorized. Upon activation, the SMR units began delivering reliable, carbon-free energy and industrial-grade steam, establishing the facility as a pioneering model for hybrid energy production in industrial settings. Across the sprawling DFW Metroplex, the emergence of hyperscale data centers began with extensive land acquisition in strategically positioned industrial parks and technology zones. These parcels were selected based on proximity to high-capacity electrical substations, dark fiber routes, and minimal exposure to flood hazards. Before vertical construction could begin, civil engineers undertook large-scale earthworks to level the terrain, compact subgrade, and construct internal roadways capable of supporting the constant delivery of construction materials, generators, and prefabricated equipment modules. With the footprint of each data center sometimes exceeding several 100,000 square feet, foundations were designed for heavy point loads, particularly under mechanical galleries and electrical rooms. Reinforced concrete mats were poured atop dense layers of engineered fill and often included embedded anchor systems for equipment skids and heavy racks. Structural steel frameworks rose rapidly using pre-assembled columns and girders, lifted by crawler cranes and joined using high-strength bolted connections. Tilt-up concrete wall panels were commonly used for perimeter enclosure, offering both speed of erection and excellent thermal and blast resistance. Roof systems were engineered with significant load allowances to accommodate air handling units and dry coolers. Steel bar joists spanned long bays, supporting a composite steel deck that received a rigid insulation layer and a fully adhered membrane roofing system. Each penetration point was pre-coordinated with mechanical, electrical, and plumbing disciplines to avoid interference and maintain weather-tight integrity. Electrical systems formed the backbone of hyperscale operations, beginning with dual utility feeds backed by on-site substations built specifically to meet the center's megawatt-scale demands. Power was stepped down through gas-insulated switchgear before being distributed via bus duct and armored cable to critical electrical rooms. Redundant, uninterruptible power supply units were housed in independent, fire-rated enclosures, with each feed isolated to maintain Tier 4 design principles. Diesel backup generators, often rated between 2 and 3 megawatts each, were installed on exterior pads with bulk fuel storage and automated day tanks. These were integrated into a site-wide power management system that allowed seamless transition during utility outages. Power distribution units and remote power panels fed rows of server racks with branch circuit monitoring for granular load balancing. Cooling infrastructure was designed for energy efficiency and fault tolerance. Indirect evaporative cooling systems, chilled water loops with centrifugal chillers, and direct expansion systems were all used depending on the operator's design preference. Cooling distribution was delivered through underfloor plenums or overhead ductwork, coordinated with containment systems that separated hot and cold aisles. CRAC and CRAH units operated in N+1 or 2 N configurations, and thermal storage tanks were added in some locations to buffer peak load conditions. Inside the white space, raised flooring was laid over pedestals anchored to the slab, allowing for airflow and cable management. Overhead trays carried fiber optic trunks, copper power conductors, and sensor cabling. Fire protection was achieved through clean agent suppression systems and pre-action sprinklers, triggered by multi-sensor detection arrays. To ensure long-term operational resilience, the commissioning process was exhaustive, including integrated systems testing and load bank simulations. As each hyperscale data center in the DFW Metroplex came online, it represented the convergence of massive power infrastructure, advanced thermal engineering, and mission-critical reliability built to serve the digital economy at scale. Launching the Austin Bergstrom International Airport expansion required a meticulously phased approach to integrate new facilities without disrupting ongoing operations. The initial stages focused on enabling works, including rerouting of utilities, relocation of existing service roads, and reinforcement of airside security perimeters. Survey crews used LiDAR and ground-penetrating radar to map existing underground infrastructure and coordinate precise tie-ins with the new systems. Temporary construction access points were established, and logistic staging areas were demarcated to accommodate a steady flow of materials, heavy equipment, and prefabricated assemblies. Foundation work for the new terminal sections, concourses, and utility buildings involved deep excavation and concrete piling. Soil conditions near the former military airbase zones necessitated dynamic compaction in some sectors to stabilize the subgrade. Once load-bearing conditions were confirmed, pile caps and grade beams were poured using high-performance concrete. Reinforcement detailing was designed to account for seismic, wind, and thermal stresses typical of large-span airport structures. The superstructure utilized a combination of structural steel framing and long-span trusses to create open interior volumes for the new concourses. Prefabricated steel components were erected using crawler cranes with sequential bolting patterns and diagonal bracing to maintain geometric alignment. Above the passenger areas, a lightweight roof system integrated insulated metal panels and skylights to introduce natural light while meeting thermal and acoustic insulation standards set by FAA and LEED requirements. Interior slab-on-deck pours were coordinated with embedded conduit runs for electrical and data distribution. Elevated mechanical mezzanines were constructed to house air handling units, VAV boxes, and ductwork runs that supplied the expanded terminal zones. HVAC systems were zoned for redundancy and integrated into the airport's existing energy management system. The use of underfloor air distribution in certain gates improved thermal efficiency and passenger comfort. New baggage handling systems were implemented beneath the terminal deck, including high-speed conveyor belts, RFID tagging stations, and inline explosives detection machines. These systems were supported by structural trenches and service catwalks, allowing maintenance crews full access during operations. The installation followed a phased commissioning schedule to maintain the functionality of existing carousels while integrating the new loops. Airside expansion included the extension of taxiways and aircraft apron areas, using Portland cement concrete pavement with deep dowel baskets and expansion joints designed for wide-body aircraft loads. Precision laser grading ensured consistent pavement elevation, and pavement marking was performed with high reflectivity thermoplastics for visibility in adverse weather. Jet bridges and ground support infrastructure were pre-installed on apron pads before gate commissioning. The new concourses were fitted with advanced security screening areas, including automated tray return systems and computed tomography scanners for carry-on luggage. Passenger amenities such as lounges, concessions, and smart wayfinding kiosks were installed with integrated digital infrastructure. This required robust Wi-Fi, Bluetooth beacon arrays, and digital signage mounted throughout the terminal core and satellite areas. To close out the expansion, life safety systems, including fire alarms, emergency lighting, and evacuation audio, were tested under full operational loads. Airport staff underwent simulation-based training in the new spaces, while system-wide performance tests validated HVAC loads, electrical grid balancing, and communications interoperability. With the completion of the expansion, Austin Bergstrom was equipped to handle future demand increases with improved passenger flow, aircraft accommodation, and operational resilience. Development of the Epic City project in Collin and Hunt counties began with an immense coordination effort across municipal boundaries, utility providers, and transportation agencies to ensure the foundational infrastructure could support the scale of this master-planned smart city. The first phase focused on land grading and hydrological management across several square miles of former farmland and low-density residential plots. Large-scale earth-moving operations utilized GPS-controlled bulldozers and motor graders to establish consistent elevation profiles for future roadways, drainage basins, and utility corridors. Extensive stormwater detention systems were constructed before any vertical development began. This included the excavation of retention ponds lined with clay and geotextile membranes, along with underground box culverts installed beneath arterial roadways to channel runoff to centralized treatment zones. Detention basins were designed with multi-stage outlet structures to regulate discharge rates during both minor and major storm events, protecting downstream ecosystems and adjacent urban infrastructure. The backbone of Epic City's build-out was its underground utility infrastructure, which included triple duct banks for electrical distribution, multi-conduit telecom pathways, and high-capacity water and sewer mains. Utility corridors were installed in coordinated trenches with separate elevation layers to avoid conflicts, and all infrastructure was mapped using RFID and GIS systems for ongoing asset management. Natural gas lines were routed with cathodic protection and above-ground isolation valves to enhance long-term safety and maintainability. The transportation grid was built from the ground up to support both traditional traffic and autonomous vehicle networks. Arterial roads featured full-depth concrete pavement with doweled contraction joints and integrated sensor arrays embedded at intersections to monitor vehicle flow and environmental conditions. Roundabouts, smart traffic signals, and vehicle-to-infrastructure communication beacons were included as part of the Intelligent Transportation System deployment. Dedicated lanes for high-occupancy vehicles, electric buses, and autonomous delivery pods were constructed alongside main boulevards using contrasting pavement materials for clear lane identification. Vertical construction followed a hybrid model of traditional steel and concrete buildings and modular prefabrication. Commercial and civic buildings were erected using steel frames and precast concrete panels, while some residential structures utilized factory-assembled wall panels and floor cassettes to speed construction cycles. Building foundations incorporated post-tension slabs in high-traffic zones and pier-supported grade beams in areas with variable soil profiles. Each district of Epic City was designed with integrated energy systems. Distributed energy resources such as rooftop solar, battery storage, and thermal energy networks were connected to a centralized microgrid, allowing for localized energy balancing and off-grid operation during outages. Substations were constructed with switchgear housed in blast-rated enclosures, and each neighborhood included EV charging stations integrated into the sidewalk infrastructure. Water reuse systems were embedded into the municipal plumbing network, with dual pipe systems carrying reclaimed water for irrigation and cooling uses. Smart metering, automated leak detection, and flow regulation valves enabled real-time water management across residential and commercial zones. Public realm enhancements included bioswale-lined streets, shaded pedestrian corridors, and precast concrete pavers with embedded LED lighting for wayfinding and safety. All components were coordinated through a centralized digital twin of the city, allowing planners, engineers, and operators to visualize, monitor, and manage the complex infrastructure in real time as Epic City rose from concept to livable urban reality. Initial groundwork for Phase 1 of the Texas LNG export terminal in Brownsville began with intensive marine and geotechnical surveys to assess the suitability of the shoreline for deepwater infrastructure. The construction site required extensive dredging operations to create a navigable ship channel and turning basin capable of accommodating LNG carriers. Cutter suction dredgers and hopper dredgers were deployed to remove millions of cubic yards of sediment, which were relocated to designated containment areas built with sheet pile enclosures and geotextile reinforcement. Onshore, the site was cleared and leveled using heavy earth-moving equipment, with special attention paid to creating stable embankments for heavy process equipment. Piling operations commenced early, with cast-in-place concrete piles driven deep into coastal clay strata to support both structural and mechanical loads. Foundation pads for the liquefaction trains, storage tanks, and auxiliary buildings were constructed using a combination of deep pile caps and heavily reinforced grade beams. The heart of the terminal, the liquefaction process units, were installed on elevated steel platforms designed to withstand hurricane-force winds and seismic events. Each train included gas pretreatment modules, cryogenic heat exchangers, and compressor skids that were prefabricated off-site and delivered via heavy haul transport. The refrigerant circuits used a combination of propane and mixed refrigerants, requiring precise installation of high alloy piping systems and high-capacity centrifugal compressors. Storage infrastructure featured full containment LNG tanks built with a pre-stressed concrete outer wall and a nickel alloy inner tank. These tanks were founded on deep mat slabs and included a suspended deck for boil-off gas handling equipment. Tank construction followed a sequential slip-forming technique for the concrete shell, while cryogenic insulation and inner tank welding were performed under tightly controlled environmental conditions. Loading infrastructure was built at the end of a new trestle-supported marine jetty. The jetty deck housed cryogenic piping, loading arms, vapor return lines, and safety systems, all supported by battered steel piles driven into the seafloor. The loading arms were installed with emergency release systems and swivel joints to accommodate tidal variation and vessel movement. Throughout the terminal, fire protection systems were deployed with high-volume deluge systems, gas detection arrays, and foam monitors at critical points. Instrumentation and control were integrated into a distributed control system housed within a blast-resistant operations center. By the end of Phase 1, the Texas LNG export terminal was equipped to handle its first liquefaction and loading operations, forming a cornerstone of US Gulf Coast LNG export capacity. Construction of the VI Resort in Glendale unfolded as a complex hospitality and entertainment project requiring meticulous sequencing across multiple concurrent workstreams. Rather than a single structure development, this resort was conceived as a multi-building campus featuring a luxury hotel tower, indoor and outdoor concert venues, water attractions, retail and dining spaces, and a central lagoon, each element demanding its own set of structural and systems engineering approaches. The site preparation phase began with mass excavation to create space for underground parking and mechanical service corridors. Soil stabilization involved lime treatment in select areas to improve load-bearing characteristics, followed by the placement of geotextile fabric and compacted fill. The lagoon basin required a deeper excavation profile, finished with a reinforced concrete liner and waterproofing membrane to contain the water feature without seepage. Adjacent utility trenches were routed to accommodate filtration lines, electrical conduits, and pump intakes, all laid in accordance with hydrodynamic modeling for optimal water circulation. The resort's signature hotel tower rose from a spread footing foundation system tied together with continuous grade beams. Above that, the structural system transitioned to a cast-in-place concrete core with post-tensioned concrete slabs, allowing for long-span floor plates and column-free views for premium guest rooms. Creep and shrinkage of the slabs were modeled early to account for deflection and ensure precise placement of embedded sleeves and anchor points for curtain wall systems. The exterior facade used a combination of unitized aluminum glazing systems and rain screen metal panels installed via swing stage access from the tower's perimeter scaffolding. Simultaneously, the concert amphitheater was constructed with a structural steel skeleton, integrating trusses that spanned the entire stage and canopy area. Acoustic isolation pads and vibration damping systems were embedded into the structure to reduce transfer to the surrounding resort zones. Back-of-house areas included electrical rooms with stage lighting control panels, audiovisual distribution rooms, and dock access for touring vehicles. Amphitheater seating was cast in place in a raked configuration with egress paths designed to flow directly into landscaped promenades. Special attention was paid to the lagoon-side entertainment areas, where boardwalks, cabanas, and overwater structures required deep-driven steel piles and precast concrete caps. These were connected by engineered wood decking that resisted UV exposure and thermal expansion. Integrated lighting and sound systems were embedded into the hardscape with low-voltage conduits routed through waterproof junction boxes mounted beneath structural supports. Mechanical and electrical systems across the site were integrated through a central utility core, with chilled water and emergency power distributed through a looped system. Energy efficiency was prioritized with variable speed drives, economizer cycles, and advanced building automation controls. Each building was modeled thermally to optimize glazing ratios, shading structures, and HVAC zoning. Kitchen exhaust systems, grease interceptors, and commercial water heaters were installed in the back-of-house areas for food and beverage operations.
From the foundation to the rooftop, every phase of the 1,000 Museum's construction demanded attention to detail, precision, and innovative engineering. It stands not just as an architectural landmark, but as a testament to what is achievable when complex geometry, structural necessity, and construction craft are woven together into a seamless vertical composition. Few transportation projects in recent American history wetlands and heavily trafficked transportation zones. From the earliest design phase, engineers had to account for a range of technical challenges, from grade separation and drainage and placing new continuous welded rail on concrete ties. The new track system was designed for higher-speed passenger operations while coexisting with freight rail, requiring the installation of upgraded ballast, drainage trenches, and reinforced embankments. Track geometry had to be in contrast. The northern portion from West Palm Beach to Orlando International Airport involved new greenfield construction through undeveloped terrain. Crews cleared and grubbed hundreds of acres, rerouted surface water channels, and installed wildlife crossings in environmentally sensitive areas. Earthwork was extensive. Embankments and cut sections were designed to minimize gradients and allow for smooth acceleration and braking curves. The right-of-way was protected by a combination of fencing, access controls, and overpasses to eliminate at-grade crossings, critical for both safety and operational efficiency. Bridges and viaducts represented key components of the alignment, especially at major road crossings and river spans. Precast concrete girder bridges were deployed using accelerated bridge construction techniques. Piers were founded on deep-drilled shafts, many of which had to be constructed under challenging conditions involving soft soils and high groundwater levels. Certain elevated sections used segmental box girders cast in place and post-tensioned, allowing for long spans and reduced support footprint. These elevated guideways also helped mitigate environmental impact in flood-prone areas and reduced the need for extensive land acquisition. One of the most technically intensive elements was the implementation of a positive train control system across the corridor. This safety-critical layer included continuous GPS-based tracking, wireless communication between locomotives and control centers, and real-time enforcement of speed limits and signal compliance. Installation of the PTC system required the placement of signal houses, transponders, and fiber optic cable across the entire alignment, with redundant power sources and cybersecurity protections. The stations themselves, including the flagship terminals in Miami and Orlando, were designed as integrated multimodal hubs. Structural systems utilized long-span steel framing, while architectural cladding included aluminum composite panels, unitized glass curtain walls, and impact-resistant fenestration. Each station featured elevated platforms to streamline boarding, high-capacity vertical circulation elements, and advanced passenger information systems. Subgrade mechanical spaces housed electrical switchgear, HVAC chillers, and water reuse systems, all connected to centralized building management controls. Rolling stock was procured with an emphasis on energy efficiency, aerodynamic performance, and crash energy management. The train sets featured articulated cars with distributed traction motors, regenerative braking systems, and pressure-sealed cabins. Maintenance facilities along the corridor were equipped with drop pits, wheel lathes, and overhead cranes to support long-term fleet servicing. Throughout construction, scheduling and logistics were as crucial as engineering. Major portions of the corridor were built in active freight environments, requiring overnight possessions and strict coordination with existing operators. In urban areas, construction teams employed traffic diversion plans, temporary decking systems, and vibration monitoring to mitigate disruption to surrounding infrastructure. Environmental compliance was maintained through erosion control plans, wildlife monitoring programs, and wetland mitigation strategies. Ultimately, the completion of the Brightline Miami-Orlando high-speed rail line stands as a testament to integrated transportation engineering, blending high-performance rail systems with modern construction methodologies. The project not only introduces a new mode of inner-city travel, but also sets a precedent for how private investment and infrastructure innovation can reshape mobility across regional scales.
The construction of the Intel semiconductor fabrication plant in Arizona, part of a multi-billion-dollar investment in domestic chip production, is a highly advanced industrial project that combines precision engineering, extreme cleanliness requirements, and massive mechanical and electrical infrastructure. Situated at Intel's existing Ocotillo campus in Chandler, this expansion adds new fabs to one of the most technologically sophisticated manufacturing sites in the world. The project supports Intel's strategy to enhance U.S. semiconductor capacity and resilience in the global supply chain, and involves the creation of highly specialized cleanroom space, support buildings, and utility systems capable of sustaining the rigorous demands of advanced chip fabrication. Site development began with large-scale excavation and grading to accommodate multiple large-footprint buildings, including cleanroom facilities, utility plants, and administrative structures. Subsurface conditions in the desert environment required over-excavation and replacement with engineered fill to achieve the uniform settlement and load-bearing capacity needed for precision manufacturing operations. Thousands of deep foundation elements, including auger cast piles and drilled piers, were installed beneath the fab buildings to isolate them from vibration and thermal expansion, both of which can interfere with nanometer-scale semiconductor production. Above the foundation level, a reinforced concrete mat slab was poured to provide a base for the fab. This slab required an extremely flat and level surface finish, with tolerances far exceeding those used in conventional construction. Specialized concrete mixes were used to control shrinkage and thermal cracking, with continuous placement operations and finishing conducted under tightly controlled environmental conditions. The superstructure of the semiconductor fab buildings was constructed using a combination of steel framing and reinforced concrete walls, designed to support the heavy mechanical loads and provide a rigid frame for the cleanroom environment. The cleanroom floors were constructed using raised access systems, which allow for the routing of process utilities, electrical conduits, and airflow distribution beneath the floor surface. These systems are supported by structural steel decks designed to limit deflection and vibration to imperceptible levels. One of the most complex aspects of the Intel fab construction is the integration of its process support infrastructure. Semiconductor manufacturing requires ultra-pure gases, deionized water, high-voltage electrical power, vacuum systems, and chemical waste handling, all of which must be delivered and maintained with absolute precision. Gigantic central utility buildings were constructed adjacent to the fab to house air compressors, chillers, scrubbers, water treatment systems, and gas cabinets. These systems feed into the fab through an intricate network of insulated stainless steel piping, double-walled chemical lines, and redundant electrical feeders, all routed through dedicated utility corridors and mechanical chases. HVAC systems for the fab are designed to maintain cleanroom conditions in accordance with ISO Class 1 to Class 5 standards, depending on the process zone. These systems involve massive air handling units that filter air through high-efficiency particulate air and ultra-low penetration air filters, delivering laminar airflow through the cleanroom ceiling. Air change rates are among the highest of any building type, and temperature, humidity, and particulate levels are continuously monitored and adjusted by automated building management systems. The cleanrooms themselves are modular in construction, with prefabricated panels used to form walls, ceilings, and integrated air plenums. Interior finishes are composed of non-shedding, electrostatically dissipative materials that resist chemical corrosion and minimize contamination risk. Workers must pass through multi-stage gowning areas, air showers, and decontamination chambers before entering these spaces, and construction crews must follow similar protocols during the fit-out phase. Electrical infrastructure is equally critical, as semiconductor fabs consume vast amounts of power with a need for extremely reliable delivery. On-site substations, switchgear, uninterruptible power supplies, and emergency generators are installed in layered configurations to support continuous operation. Power quality is managed through real-time monitoring and conditioning systems to prevent voltage fluctuations or outages that could compromise sensitive fabrication tools. Process tool installation represents a major component of fab construction. These tools, which include photolithography scanners, etchers, ion implanters, and chemical vapor deposition chambers, are extremely sensitive and must be installed on vibration-isolated foundations with precise alignment. Tool hookup involves hundreds of connections for process gases, liquids, vacuum, and data communications. Each tool is commissioned individually and tested extensively before being certified for production. To manage water use, the site features a cutting-edge water reclamation plant that recycles process water for reuse in cooling towers and rinse processes. This system is critical in Arizona's arid climate and is one of the most advanced water sustainability efforts in industrial manufacturing. Waste treatment systems also neutralize and separate chemical byproducts for proper disposal, in compliance with federal and state environmental regulations. Construction was carried out using lean methodologies and building information modeling, enabling real-time coordination between trades and minimizing clashes between complex mechanical systems. Prefabrication was employed extensively for piping racks, electrical skids, and modular wall panels to accelerate installation and reduce site congestion. With thousands of workers on site daily, logistics were managed using zone scheduling, digital tracking, and real-time communication tools to maintain progress and safety. Where a coal-fired power plant once dominated the landscape in Moapa, Nevada, the construction of the Reed-Gardner battery storage system marked a shift toward clean energy storage and grid stabilization. The first phase of the project began with demolition and site remediation,
existing utility corridors, concrete pads, and buried infrastructure from the retired power plant had to be removed or repurposed. Soil testing and grading ensured that the land met the geotechnical requirements for placing a large array of battery enclosures and associated electrical equipment. Once the site was prepared, the foundation work proceeded with a modular strategy. Each battery container, typically the size of a shipping container, rested on reinforced concrete pads designed to bear static loads while allowing thermal expansion. These pads were poured with integrated cable trenches and embedded conduits for power and control wiring. The layout followed a linear alignment to optimize airflow, simplify maintenance access, and facilitate short routing to the power conversion systems. The energy storage units themselves consisted of lithium-ion battery cells housed in steel containers with integrated fire suppression, HVAC, and thermal monitoring systems. These containers arrived pre-assembled and were offloaded using mobile cranes or forklifts, then anchored in place with structural hold-downs. Adjacent to each group of battery containers, power conversion systems were installed, which included bidirectional inverters, transformers, and medium-voltage switchgear. These systems allowed the batteries to interface with the regional grid, converting stored DC energy into AC power during peak demand periods and drawing excess electricity during off-peak times. Cable terminations and system integration require detailed coordination. High-voltage AC and low-voltage control wiring were routed through separate underground duct banks to minimize interference. Grounding grids were installed beneath the entire array, bonded to each enclosure and system cabinet to ensure personnel safety and lightning protection. The site also included perimeter fencing, surveillance, and access control in compliance with NERC reliability and cybersecurity standards. A supervisory control and data acquisition system tied all battery enclosures, inverters, and transformers into a centralized control hub. Fiber optic links and programmable logic controllers enabled real-time monitoring of temperature, voltage, current flow, and system health. In addition to the core storage function, the installation featured black start capabilities and reactive power support to bolster grid stability during contingency events.
Launching the Scottsdale Optima McDowell Mountain Village meant executing a large-scale, multi-building residential and mixed-use development in a sensitive desert environment, where sustainability, structural innovation, and logistical precision had to align from day one. Unlike conventional suburban construction, this project followed an integrated design-build model that required close coordination between architectural vision and structural implementation, from schematic design through vertical completion. Construction began with extensive site grading across the large footprint, but it also incorporated bioswale integration and retention basins to manage stormwater naturally. Earthwork included over-excavation beneath all building pads, followed by moisture conditioning and recompaction to meet strict geotechnical tolerances. Trenching for deep utilities came next, with parallel routing for chilled water, domestic water, fire protection, sewer, storm, and dry utilities such as power and communications. These were run in pre-planned corridors to serve each building efficiently without unnecessary excavation duplication. Optima's construction model leverages cast-in-place concrete systems extensively, and this village was no exception. Each residential tower utilized a Podium Plus configuration, with subterranean parking garages acting as structural base levels. These below-grade levels were waterproofed with bentonite sheets and fluid-applied membranes before forming walls with high-density plywood systems. Vertical columns and shear walls extended through the podium to support the elevated post-tensioned slabs above. These slabs were poured in sequence using high-strength concrete, tensioned after curing to reduce cracking and allow thinner slab profiles, thereby reducing structural dead load and permitting taller floor-to-ceiling heights. Vertical cores for stairs, elevators, and utilities were slip-formed to accelerate progress, allowing parallel trades to begin rough-ins shortly after slab placement. Once the podium was completed, tower levels were constructed floor by floor in a tightly managed schedule. Mechanical, electrical, and plumbing trades were embedded early in the structure, using sleeve boxes, conduit blockouts, and prefabricated pipe racks lifted into place by tower crane. All ductwork was modeled using clash detection software, and fire-rated assemblies were coordinated with penetrations for seamless inspection approvals. Perhaps most distinctive was the incorporation of extensive rooftop gardens and planted balconies, all of which required complex structural planning to support soil loads, waterproofing protection, and integrated irrigation systems. A layered green roof assembly included root barriers, drainage mats, lightweight planting media, and capillary irrigation tubing tied to centralized water treatment systems that filtered grey water for non-potable reuse. Glazing systems were high-performance, thermally broken aluminum frames with low emissivity glass, designed to optimize daylighting while minimizing solar gain. Operable windows were integrated throughout, paired with sunshades, trellises, and balconies that added passive cooling elements. Exterior finishes blended textured concrete, steel mesh panels, and composite cladding materials, applied using suspended swing stages and mast climbers. Interior units followed a luxury specification with radiant floor heating systems embedded in gypcrete topping slabs, integrated lighting control systems, and floor-to-ceiling window walls. Amenities such as fitness centers, lap pools, spa zones, co-working lounges, and automated parking systems were incorporated directly into the podium and terrace levels, requiring close coordination between structural, architectural, and specialty contractors. All buildings were tied together with a shared energy and connectivity spine, linking data, security, fire alarm, and mechanical system controls through a centralized plant and digital management hub. The result was a self-contained, high-density residential complex that not only met structural and livability goals, but elevated the standard for sustainable urbanism in the Scottsdale region.
In the heart of downtown Miami, where the skyline rises in a collage of glass towers, 1000 Museum distinguishes itself not just by height, but by the extraordinary engineering involved in bringing its organic exoskeleton form to life. Long before any concrete was poured, the project demanded a fundamental rethinking of conventional tower design due to the decision to incorporate a curvilinear external structural system. The concept required that the building's primary structural support come from its exterior, a dramatic departure from the more common internal core and column system used in most residential high-rises. The foundation phase began with the installation of deep drilled shafts extending over 100 feet into Miami's sedimentary bedrock. These shafts were reinforced with heavy steel cages and trimly poured concrete to form a stable load path beneath the structure's core and its unique perimeter support zones. Above ground, the ground-level mat foundation included thousands of cubic yards of high-strength concrete, placed in continuous pours to avoid cold joints and ensure structural uniformity. The mat, several feet thick, had to be completed in multiple stages, each meticulously scheduled to coordinate pump trucks, concrete deliveries, and rebar placement. Skeleton became the central construction challenge. Rather than simple vertical columns, the perimeter frame was made up of sweeping biomorphic curves that branched and intertwined as they moved up the tower. This required a custom formwork system, fabricated off-site and assembled on-site in pieces, with tolerances often within a fraction of an inch. The forms had to be modified on a floor-by-floor basis due to the shifting geometries, and concrete placement was done in segments with continuous quality monitoring to prevent honeycombing or segregation within the curved shapes. This allowed the interior spaces to be more open and flexible, eliminating the need for many internal columns. Because the exoskeleton was exposed to the elements, its surface quality had to meet both structural and architectural criteria, requiring special attention during finishing, building loads at the highest elevation, along with wind load modeling to ensure rotor wash would not affect facade elements or roof equipment. Below the helipad, mechanical systems including chilled water plants and emergency generators were installed in hardened enclosures, isolated acoustically and vibrationally to avoid disturbing the building's luxury residential interiors. The glass curtain wall system was also a vital piece of the project. It had to be installed around the branching exoskeleton while maintaining weather tightness and minimizing air infiltration. Each panel was custom-shaped and tested for wind resistance, particularly given the building's exposure to hurricane-force conditions. Installation teams used specialized lifting rigs and sequencing plans to coordinate around the exoskeletal nodes, many of which intersected the glass modules in non-linear ways. Elevator and life safety systems adhere to elevators and pressurized stairwells. The building featured advanced smoke evacuation systems and a full backup power architecture integrated into the overall structural system.
The GreenLink West transmission line is a major electrical infrastructure project in the state of Nevada, designed to enhance grid reliability, support renewable energy integration, and increase transmission capacity across the western region of the state. Developed by NV Energy, this transmission corridor spans approximately 300 miles, connecting the Las Vegas area in the south to the Fort Churchill substation near Yerington in the north. The project represents a foundational component of Nevada's broader GreenLink Nevada initiative, intended to transform the state's electrical grid and facilitate access to clean energy resources while improving resiliency and operational flexibility. Construction of the GreenLink West project begins with detailed route planning and environmental assessment, as the alignment traverses vast expanses of public and private land, including Bureau of Land Management territory, tribal lands, and rural communities. Environmental permitting requires in-depth analysis of habitats, cultural resources, hydrology, and visual impacts. Once regulatory approvals are secured, fieldwork starts with land surveying, geotechnical borings, and the establishment of construction access routes. The transmission line itself is a high-voltage 525 kilovolt alternating current system, using steel lattice towers and monopole structures, depending on the terrain and land use considerations. The design of the transmission line takes into account topography, wind loading, seismic considerations, and conductor sag. In mountainous areas, lattice towers are selected for their ability to span long distances and provide greater stability. While in open desert or agricultural zones, tubular steel monopoles are often preferred for their smaller footprint and faster installation. Foundation construction for each transmission structure is highly site-specific. In rocky or uneven terrain, drilled pier foundations are used, where holes are bored into the ground and filled with reinforced concrete. In softer soils, direct embed foundations or grouted steel shafts may be employed. Reinforcing steel cages are fabricated and placed on-site, with concrete delivered by ready-mix trucks or mobile batch plants established along the corridor. Anchor bolts are set with tight tolerances to ensure the precise alignment of tower base plates. Tower erection involves lifting pre-assembled sections using crawler cranes, hydraulic booms, or helicopter lifts in remote or inaccessible areas. Each tower section is bolted together in sequence, and alignment is checked at each stage. Conductor stringing follows tower installation and is conducted using tensioning and pulling equipment to carefully manage the weight and sag of the heavy aluminum conductor steel reinforced cables. Multiple phases of conductors are strung along with shield wires for lightning protection, and optical ground wires are installed to enable real-time monitoring and communications. Substations at each end of the GreenLink West line are upgraded or newly constructed to accommodate the increased voltage and new circuit paths. At these substations, high-voltage breakers, transformers, reactors, and switchgear are installed on reinforced concrete pads, protected by gravel surfacing and perimeter fencing. Buswork, insulators, and control cabling are arranged to allow for flexible operation and maintenance, and relay protection systems are programmed to detect faults and isolate them within milliseconds. To support future energy development, tap points and interconnection bays are integrated into the transmission design, allowing new solar, wind, and geothermal projects in central and western Nevada to tie directly into the grid. The transmission line is also engineered with N1 reliability criteria, meaning the system can continue operating even in the event of a single component failure, an essential feature for ensuring consistent power delivery in extreme weather or emergency conditions. Throughout construction, environmental mitigation measures are implemented to protect wildlife, water quality, and cultural resources. This includes installing erosion control barriers, wildlife exclusion fencing, and temporary bridging at stream crossings. Dust suppression is carried out with water trucks, and sensitive areas are avoided or monitored with environmental inspectors present during construction. When work is completed, disturbed areas are regraded and revegetated with native plant species to restore habitat and minimize erosion. Workforce logistics are a significant consideration given the remote nature of much of the route. Mobile staging yards, equipment laydown areas, and temporary access roads are established at intervals to support material delivery and worker access. Helicopter operations are scheduled to transport components and personnel to difficult-to-reach locations, especially in rugged mountainous zones where road access is limited or environmentally restricted. Digital construction management tools, including GIS-based routing systems, remote sensing data, and real-time construction monitoring platforms, are employed to coordinate crews, document progress, and track compliance with safety and environmental requirements. A central command center oversees construction phasing and coordinates with utility operations to avoid service disruptions and ensure synchronization with other grid infrastructure projects.
Construction of the Brightline West high-speed rail begins not with rails, but with an extensive corridor preparation effort stretching along the Interstate 15 right-of-way between Southern California and Las Vegas. The alignment was selected to leverage existing transportation corridors, minimizing environmental impact while reducing the need for new land acquisition. Survey teams marked out the route using GPS-based geolocation, after which clearing and grubbing crews removed desert vegetation and leveled the alignment in preparation for subgrade construction. Due to varying soil conditions, crews implemented soil stabilization techniques such as cement treatment and moisture conditioning to achieve the compaction required for long-term settlement resistance. The rail substructure comprises several layers, beginning with compacted subgrade, followed by engineered fill, and a layer of ballast in zones where traditional track is used. However, in high-speed segments, especially those reaching over 180 miles per hour, a concrete slab track system will be utilized. This involves pouring continuous reinforced concrete slabs with expansion joints and embedded fasteners designed to hold the rail in place with millimeter-level precision. These slabs are set atop geotextile membranes and drainage systems to prevent water infiltration and thermal heave. Bridges and viaducts form a critical part of the project, particularly where the line crosses over existing roadways or environmentally sensitive terrain. Precast concrete girders are transported via specialized haulers and lifted using high-capacity gantry cranes. Abutments and piers are constructed using drilled shaft foundations, with rebar cages tied on site and lowered into the shafts before concrete placement. In seismic zones, isolators and energy-dissipating devices are installed to ensure structural resilience during earthquake events. Catenary systems for electric power delivery require the installation of overhead contact system, poles spaced at precise intervals along the corridor. These poles are anchored in concrete footings and support tensioned copper conductors delivering 25 kilovolts AC. Power substations are built at strategic intervals, converting utility-scale electricity to the necessary specifications for the trains and feeding the system through switchgear and protection circuits. Stations are designed as intermodal hubs, integrating ticketing systems, security screening, vertical circulation, and baggage handling. Platform edge doors, vibration-damping structural slabs, and acoustically treated canopies are incorporated to ensure comfort and safety at high-speed boarding conditions. All systems are tied into a centralized traffic control center that uses fiber optic networks and redundant data links for command, monitoring, and dispatch. Brightline West aims to redefine regional travel by delivering a fully electric, high-capacity corridor built with exacting civil and systems integration standards tailored for American infrastructure.
With healthcare rapidly advancing, the expansion of the Mayo Clinic campus in Phoenix required a highly coordinated approach to medical facility construction on an active site. Rather than developing on a greenfield, this project had to integrate new structures, towers, treatment areas, surgical suites, and utility cores into a functioning hospital environment without disrupting ongoing clinical operations. One of the first construction challenges was establishing a secure and phased logistics plan. Construction zones were partitioned from patient access routes using temporary fencing, directional signage, and sound attenuating barriers. Materials and equipment deliveries were tightly scheduled during off-peak hours, and tower crane operations were restricted to specific times to avoid interference with medical helicopter flight paths. Early enabling work involved the relocation of existing utilities, including domestic water lines, oxygen and medical gas conduits, and high-voltage electrical feeders, all of which had to be rerouted through temporary above-ground bypasses to maintain uninterrupted service. Structural systems for the hospital towers used a cast-in-place concrete frame with post-tension slabs, enabling open interior spans suited to evolving clinical layouts. The concrete mix was carefully designed for rapid strength gain to maintain construction pace, with high early strength additives and thermal control measures to avoid cracking. Columns were formed with reusable modular formwork, while floor plates were poured in large sequences using pump trucks and placing booms. Seismic detailing was embedded into shear walls and core walls, given the region's moderate seismic classification and the facility's essential use designation. Mechanical, electrical, and plumbing systems were among the most intricate components of the expansion. A centralized mechanical plant was expanded with additional chillers, boilers, and air handling units, each set on isolated inertia bases to limit vibration transmission to clinical environments. Mechanical penthouses and interstitial floors allowed for horizontal distribution of large ductwork, steam, condensate return, and reverse osmosis water piping. Extensive MEP coordination was performed through clash detection using 3D BIM modeling, ensuring ceiling plenums remained serviceable while also complying with stringent infection control requirements. Medical gas systems were extended from new bulk storage tanks through stainless steel piping networks with orbital welded joints, each one subject to 100% radiographic inspection. Redundant power was supplied by new diesel generator banks, paralleled with existing infrastructure, and backed by automatic transfer switches and battery UPS systems located in dedicated electrical rooms. Isolation panels, surge protectors, and clean power transformers were also installed for sensitive imaging equipment. Interior construction was sequenced to align with medical equipment installation schedules. Lead-lined walls and shielded ceilings were placed in radiology and surgical rooms, while vibration-isolated slabs and RF shielding were installed in MRI suites. Finishes included seamless epoxy flooring, antimicrobial wall protection, and hospital-grade ceiling systems with integrated lighting and air diffusers. Infection control risk assessments governed every phase, with negative pressure containment zones, HEPA filtration, and daily clean protocols enforced throughout active areas. Exterior elements incorporated high-performance glazing, architectural precast panels, and metal screen walls to conceal rooftop equipment. Site work included new patient drop-offs, staff parking, and ambulance circulation paths, all coordinated with civil stormwater infrastructure and ADA-compliant design. Ultimately, the Mayo Clinic Phoenix expansion merged complex medical infrastructure with construction excellence to produce a world-class facility that continues to evolve in parallel with modern healthcare delivery.
Rebuilding from near-total devastation, the reconstruction of Tyndall Air Force Base following the impact of Hurricane Michael in 2018 required a complete reimagining of military infrastructure in the face of extreme climate events. The project began with an intensive demolition and debris removal phase, where thousands of tons of structural wreckage, downed trees, and contaminated materials were cleared using heavy equipment including hydraulic excavators, high-reach loaders, and roll-off trucks. Before any vertical construction resumed, environmental remediation teams had to address storm-related hazardous material spills and groundwater contamination risks. Once the site was stabilized, the reconstruction effort shifted toward creating a base of the future, grounded in resilience, energy efficiency, and smart infrastructure. One of the foundational strategies was the implementation of mission-driven zoning, in which facilities were grouped by operational function: flight line, support, administrative, residential, allowing for optimized utility distribution, vehicular movement, and force protection measures. Civil engineers realigned roadways, constructed new perimeter security systems, and raised the elevation of key buildings to avoid future storm surge damage. The new construction used tilt-up concrete panels and hurricane-rated curtain wall systems across most structures. Load-bearing walls were designed to resist sustained winds exceeding 180 miles per hour, and all roofs were anchored with enhanced uplift connectors and continuous load paths to transfer forces to the foundation. Building envelopes included closed-cell spray foam insulation and thermally broken aluminum fenestration systems to improve energy performance while maintaining blast resistance in mission-critical zones. A major focus of the reconstruction was integrating advanced electrical microgrid systems. Redundant power generation sources, including solar PV arrays, diesel generators, and battery storage, were installed to ensure operational continuity during grid outages. Subsurface duct banks were rerouted and reinforced to improve storm resilience, and switchgear facilities were elevated above base flood elevation to avoid future water intrusion. Hangar complexes for F-35 aircraft required particularly high-precision construction tolerances. These steel-framed structures incorporated massive rolling hangar doors, anti-static flooring systems, and integrated fire suppression systems specifically engineered for jet fuel hazards. Mechanical systems included custom air handling units with high filtration capabilities to protect both personnel and aircraft maintenance environments. Drainage was redesigned with sustainability and resiliency in mind. Bioswales, reinforced outfalls, and permeable pavements were incorporated to improve stormwater quality and reduce erosion. Stormwater retention basins were expanded and linked to smart monitoring systems that automatically adjust outflows based on weather forecasts and rainfall events. The reconstruction also deployed extensive building automation systems across administrative and housing facilities. Lighting, HVAC, and security systems are now centrally controlled and monitored, allowing real-time energy optimization and system diagnostics. Residential zones were rebuilt to meet LEED Silver and above standards, using impact-resistant windows, high-efficiency HVAC units, and low-flow plumbing fixtures.
The Related Santa Clara project is a major urban development initiative in Northern California, transforming a former landfill site near Levi's Stadium into a dynamic mixed-use district. Envisioned as a dense urban hub blending residential, commercial, retail, entertainment, and hospitality components, the project spans over 200 acres and represents a model of large-scale master planning, sustainable design, and complex site engineering. Given its scale and the geotechnical challenges of building on a capped landfill, the construction of Related Santa Clara required significant groundwork before vertical development could begin. Site development began with environmental remediation and geotechnical stabilization. The site had a history as a municipal landfill, necessitating the construction of an engineered cap to seal the waste material and prevent leachate migration. This cap consisted of layers of compacted clay, geomembranes, geotextiles, and protective cover soils. Before any structures could be built, the cap was inspected, reinforced where necessary, and overlaid with an elaborate system of gas venting and groundwater monitoring wells. Methane gas mitigation was a critical component of the design, with horizontal collection pipes, vertical extraction wells, and passive venting systems embedded beneath proposed building footprints. Given the risk of differential settlement on such fill material, structural design strategies emphasize shallow, flexible foundations for low-rise buildings and deep pile-supported foundations for taller structures. Load-bearing elements were designed with settlement tolerances in mind, and slab-on-grade floors were decoupled from building frames using isolation joints and subgrade void forms. All utilities and infrastructure conduits were routed in flexible, jointed systems to accommodate ground movement, with multiple access points for maintenance and inspection. Horizontal infrastructure development was extensive, involving the construction of new roads, water mains, stormwater systems, and electrical networks. The street grid was laid out to prioritize walkability and multimodal access, with curbless shared streets, wide sidewalks, and dedicated bike lanes. Stormwater management relied on a network of bioswales, underground detention vaults, and permeable pavements designed to meet stringent regional stormwater discharge regulations while promoting on-site infiltration and groundwater recharge. One of the most complex components of the project was the construction of a central utilities plant and microgrid. This facility provides heating, cooling, and electricity distribution across the entire development using a district energy model. Chillers, boilers, thermal storage tanks, and backup generators are housed in a central structure connected to a network of underground utility corridors. These corridors carry chilled water, hot water, and electrical conduits throughout the site, reducing the need for decentralized mechanical systems and improving energy efficiency at scale. As vertical construction commenced, buildings were erected using a range of framing systems tailored to their use and height. Mid-rise residential buildings typically used post-tensioned concrete podiums supporting wood-framed or light-gauge steel superstructures, while office towers and hotels employed structural steel or reinforced concrete frames with shear walls and lateral bracing. Floor slabs were designed for flatness and serviceability, with embedded sleeves and core-drilled openings to accommodate MEP installations. Facade systems across the development included high-performance glazing, precast concrete panels, metal cladding, and fiber cement rain screens, all selected for durability and aesthetic variety. Building envelopes were constructed with continuous insulation, air barriers, and vapor retarders to meet California Title 24 Energy Code requirements. Roofs were equipped with reflective membranes, green roofing elements, and photovoltaic arrays tied into the site-wide energy monitoring system. Interior fit-outs varied depending on building type, but generally featured open-plan layouts with raised access flooring and modular wall systems in commercial spaces. Residential units were built with acoustic-rated wall assemblies, energy-efficient appliances, and low-flow plumbing fixtures. Retail shells were delivered with basic utilities stubbed to tenant spaces, allowing for customization during future tenant improvements. Open space and landscape architecture played a central role in the master plan, with a significant portion of the site dedicated to parks, plazas, and pedestrian corridors. Structural soil cells were installed beneath sidewalks to support street tree root growth and promote long-term canopy development. Irrigation systems used non-potable water sourced from a recycled water facility and monitored by smart controllers for efficiency. Public art installations, integrated lighting, and site furnishings were deployed to enhance usability and identity across the district. Transportation infrastructure included structured parking garages, transit shuttle drop-offs, and future-proofed provisions for autonomous vehicle integration. All parking structures featured EV charging stations, with conduits sized for future capacity increases. Bicycle storage rooms, lockers, and repair stations were incorporated into each block to support active transportation. Throughout construction, logistics were tightly managed to coordinate multiple contractors working across different zones. Site-wide scheduling tools, digital modeling, and construction sequencing simulations ensured that trades did not interfere with each other and that materials were delivered just in time. Erosion control measures, dust suppression systems, and noise barriers were enforced to minimize environmental impacts on neighboring communities and sensitive habitats along the nearby Guadalupe River corridor.
Shifting focus to one of the most significant sports construction projects in recent American history, Allegiant Stadium in Las Vegas began with an enormous excavation effort to prepare the site just west of the Strip. The soil conditions required pre-treatment due to high water tables and loose granular fill. To stabilize the subgrade, contractors used deep soil mixing and installed wick drains to accelerate consolidation. Once the pad was secured, work commenced on the foundation, which incorporated hundreds of drilled piers and massive concrete footings to support the superstructure. The building's primary frame featured a combination of steel trusses and precast concrete components. One of the defining features of the stadium, the sweeping roof canopy, was enabled by a network of long-span steel trusses, each weighing several hundred tons. These elements were fabricated off-site and delivered in sequential shipments, where they were assembled using gantry cranes and specialized rigging equipment. The roof itself was a cable-supported ETFE system that demanded meticulous tensioning and anchorage precision to accommodate thermal movement and wind uplift. Inside, the seating bowl was configured with precast raker beams and vomitory walls, each piece carefully aligned to maintain sightlines and support tiered loads. The lower bowl was cast in place, while the upper levels were constructed using a combination of steel risers and precast planks. Mechanical systems were housed in interstitial levels between the concourses and integrated into the structure to reduce noise and vibration transmission. One particularly ambitious component of the project was the operable field tray. Designed to support natural grass for NFL games, the tray rested on a series of rails embedded in the foundation slab. It could be rolled in and out of the stadium using hydraulic motors and steel wheel assemblies, weighing several million pounds in total. This required structural coordination with the surrounding apron and subgrade drainage systems, which had to accommodate both static and dynamic loads without settlement. Facade construction involved a high-performance curtain wall system clad in black fritted glass and metal panels. Behind this outer skin, wind bracing and thermal barriers were integrated to manage the desert climate. Each section of the envelope was panelized off-site and installed via mobile cranes in a rapid sequence, closing in the building in time for interior finishes to commence. Allegiant Stadium represents a convergence of speed, scale, and innovation completed on a fast-track schedule that demanded round-the-clock coordination across hundreds of trade contractors.
Not every freeway expansion challenges engineers with such extreme topographic variation as the Interstate 17 Black Canyon Freeway widening. This project, traversing from North Phoenix up through mountainous terrain toward Flagstaff, required overcoming both urban congestion constraints and rural geological complexities. It was not a uniform widening effort. Rather, it entailed a hybrid approach of adding general-purpose lanes, climbing lanes for freight vehicles, and in some segments, reversible flex lanes designed to accommodate peak traffic flow. Construction sequencing began with extensive earthwork, particularly through the northern sections where cuts into basaltic rock were necessary. Controlled blasting operations were scheduled in tightly regulated windows to reduce traffic disruption and environmental impact. Each blast zone underwent pre- and post-blast surveys to ensure rock stability and confirm that the blast radius remained within safety thresholds. Debris was excavated using high-reach excavators and loaded into articulated dump trucks for repurposing as fill in adjacent embankment zones. These embankments were constructed in compacted lifts, each tested for moisture content and density to meet strict compaction standards necessary for load-bearing capacity. In the more urbanized southern corridor, work was performed in narrow medians and shoulders. Traffic staging required temporary barrier placement, restripping, and real-time signal adjustments to maintain throughput while isolating work zones. Construction of new lanes meant full-depth pavement installation, beginning with subgrade preparation, placement of aggregate base course, and then successive lifts of asphaltic concrete. The mix design was tailored for durability in high-temperature conditions, incorporating polymer-modified binders and performance-graded asphalt to resist rutting and thermal cracking. Bridges posed a significant element of the widening effort. Many existing structures over washers and arterial roads were widened symmetrically using cast-in-place concrete decks over precast, pre-stressed concrete girders. Abutments and piers were reinforced with drilled shaft foundations, extending deep into competent bedrock to mitigate differential settlement. Expansion joints, bearing pads, and shear keys were detailed to accommodate seismic and thermal movements while maintaining deck continuity. Stormwater management infrastructure was upgraded in tandem, involving the installation of reinforced concrete box culverts and oversized pipes beneath the widened footprint. In some areas, detention basins were excavated with engineered outlet structures to manage discharge rates and protect downstream properties from flooding. Erosion control measures, including soil binders, riprap armoring, and hydro seeding were deployed along slopes and drainage channels as permanent stabilization. Intelligent transportation systems were embedded throughout the corridor. This included dynamic message signs, closed-circuit TV cameras, radar-based traffic sensors, and fiber optic communication backbones. These systems were linked to the Regional Traffic Operations Center, enabling real-time monitoring and adaptive traffic management, particularly useful for managing incidents and peak period congestion. Guardrail systems, median barriers, and high visibility signage were installed during the final phase. Road striping used thermoplastic materials with reflective beads for enhanced night visibility. Before opening, each section underwent load testing, profile evaluation, and friction testing to ensure geometric and safety compliance.
Beneath the surface of Biscayne Bay, the Port of Miami Tunnel represents one of the most complex underwater infrastructure undertakings in the southeastern United States. Constructed to alleviate downtown Miami's chronic congestion caused by thousands of daily truck trips to and from the port, this project required advanced tunneling methods, massive marine coordination, and exacting safety systems. The overall plan was to connect the MacArthur Causeway directly to Port Miami via twin tunnels, each approximately 3/4 of a mile in length, buried beneath the seabed and designed to handle bidirectional vehicular traffic. Before tunneling could begin, preparatory works focused on dredging and stabilizing the soft bay soils. Extensive geotechnical investigations were conducted using boreholes and cone penetration tests to classify the variable limestone and sand strata that would be encountered. Ground improvement methods such as jet grouting and ground freezing were considered in preliminary phases, but the design ultimately relied on a pressurized face tunnel boring machine capable of navigating both soft ground and denser rock formations. Custom built in Germany and shipped in segments, the TBM used on this project was over 40 feet in diameter and weighed several hundred tons. Assembly took place in a large launching pit on Watson Island, where reinforced concrete diaphragm walls and a trimmy-placed base slab formed the structural cradle. The boring process progressed incrementally, with the TBM advancing just a few feet per hour, while simultaneously installing precast concrete segment rings behind it to form the tunnel lining. These segments, fabricated off-site and transported to the launch area, were equipped with waterproof gaskets and dowel interlocks to ensure tight seals under hydrostatic pressure. The tunnel alignment passed beneath the shipping channel, which introduced unique challenges related to buoyancy, water ingress, and structural reinforcement. At the deepest sections, the tunnel crown lay more than 100 feet below the water surface. To resist both groundwater pressure and seismic loading, the tunnel lining thickness and steel reinforcement were increased, especially at the crown and invert where stress concentrations were highest. Real-time instrumentation inside the TBM provided feedback on ground conditions, face pressure, and segment placement accuracy, helping to mitigate risks of sinkholes or blowouts. Simultaneously, surface-level works included the construction of ventilation buildings at each portal. These reinforced concrete structures house massive axial fans, emergency backup power systems, and life safety controls. Each tunnel is equipped with a full suite of fire suppression systems, including deluge sprinklers and fire-rated wall finishes. A network of electronic signage, CCTV, and incident detection sensors runs the entire tunnel length, all connected to a centralized control room staffed continuously. Upon completion of tunneling, crews moved on to road deck construction, lighting installation, and system commissioning. Pavement was laid using specialized low-sag asphalt mixes designed to withstand constant vehicle loading in a confined environment. Final testing included simulated fire events, emergency evacuation drills, and full-scale load testing to ensure operational readiness.
The redevelopment of Terminal 1 at John F. Kennedy International Airport is a major aviation infrastructure initiative designed to transform the aging terminal into a state-of-the-art global gateway. Scheduled for completion in 2025, the new Terminal 1 will significantly expand capacity, modernize facilities, and enhance the passenger experience through a comprehensive overhaul of terminal architecture, airside and landside access, and critical systems. This $9.5 billion project is being constructed on the sites of the former Terminal 1, Terminal 2, and the former Terminal 3, requiring an intricate phased demolition and construction process to keep the airport operational throughout the redevelopment. The first major phase involved the demolition of old structures, including the entirety of Terminal 2. Given the operational context of an active airport, demolition was performed in a highly controlled environment. Work included asbestos abatement, removal of outdated mechanical systems, and structural dismantling carried out in sequence zones to maintain safety and minimize impact on adjacent runways and taxiways. Materials were sorted for recycling and disposal, with concrete crushed on site for reuse as fill-in subgrade construction. Following demolition, site preparation included soil stabilization and grading across the expansive redevelopment footprint. The new terminal is built on a reinforced mat foundation system, consisting of deep piles socketed into dense subsoil layers to counter settlement and lateral loads. Pile caps and ground-level slabs were poured in stages, using high-strength concrete and admixtures tailored to airport-grade durability requirements. Ground improvement techniques, including vibrocompaction and surcharge preloading, were employed to stabilize, fill, and mitigate long-term settlement risks, especially in areas adjacent to active taxiways. The superstructure of the terminal is being constructed with a combination of steel framing and reinforced concrete cores. The design emphasizes long-span steel trusses in the main check-in hall and departure areas to allow for wide-open spaces without intermediate columns. These trusses are fabricated off-site and erected using crawler cranes during low traffic periods, coordinated with Port Authority and air traffic control to maintain safety. Reinforced concrete shear walls and elevator cores provide lateral stability and house the terminal's mechanical and vertical transportation systems. The new Terminal 1 will span over 2 million square feet, incorporating up to 23 wide-body aircraft gates upon full build-out. To accommodate this, the apron and aircraft parking areas are being reconstructed with concrete pavements rated for Group 5 and 6 aircraft. Subsurface drainage systems, fuel hydrant lines, and de-icing fluid containment infrastructure are being installed beneath the apron. Jet bridges, preconditioned air systems, and ground power units are integrated into each gate position to streamline aircraft turnaround operations and reduce emissions. The terminal building itself is designed with a high-performance facade, using double-glazed curtain wall systems with low emissivity coatings and integrated sunshades. These systems not only reduce solar heat gain, but also create a visually open and naturally lit interior environment. Roof structures are insulated and built to accommodate photovoltaic panels, contributing to the terminal's sustainability goals. Inside, the passenger processing zones are being built with modular and flexible layouts. The check-in hall includes self-service kiosks, bag drop counters, and high-capacity conveyor systems feeding into a next-generation baggage handling system. This system uses automated sorters, inline explosive detection machines, and robotic diverters to ensure both security and efficiency. The departures area includes centralized security screening with advanced CT scanners and automated tray return systems. The terminal's concourses are being built to accommodate retail, dining, and lounge spaces along with circulation corridors. Structural framing is designed to allow flexibility for future reconfiguration, with raised floors in select areas to support changes in mechanical and electrical distribution. Passenger movement is facilitated by moving walkways, elevators, and escalators, while lighting, air conditioning, and signage systems are controlled by a centralized building management platform. Mechanical, electrical, and plumbing systems are distributed from dedicated utility rooms located in basement and rooftop levels. The HVAC system includes high-efficiency chillers, thermal storage tanks, and air handling units with demand-controlled ventilation. Plumbing systems are outfitted with leak detection, low-flow fixtures, and hot water recirculation pumps to reduce consumption. Electrical infrastructure includes dual power feeds from independent substations, backed by diesel generators and battery storage systems for uninterruptible power supply to critical systems such as air traffic communications, baggage handling, and security equipment. Landside access is being completely reconfigured as part of the redevelopment. This includes new roadways for private vehicles, commercial transport, and shuttle buses, along with expanded curbside drop-off and pickup zones. New parking structures are being built with integrated wayfinding, EV charging stations, and real-time space monitoring systems. Pedestrian bridges are constructed to link parking and transit hubs directly with terminal levels, allowing safe and efficient passenger flow across busy traffic zones.
Rising from the arid landscape of Story County, Nevada, the Gigafactory Nevada was conceived as a cornerstone of Tesla's ambition to revolutionize battery production at an unprecedented scale. Construction began with extensive earthworks to level the undulating terrain. The site, chosen for its proximity to rail lines and major highways, required vast quantities of excavation and grading. Bulldozers and graders reshaped the desert floor, while stormwater management systems were installed to direct runoff during rare but intense rainfall events. Once the pad was prepared, engineers focused on laying the foundation. Due to the immense footprint, eventually designed to exceed over 13 million square feet, the slab had to be poured in meticulously scheduled phases. Reinforced concrete was poured in segmented pours, each with embedded conduits and anchor bolts for future equipment. The structural frame was composed of prefabricated steel columns and trusses, delivered in sequenced shipments and lifted into place with crawler cranes. Crews worked in rotating shifts to maintain continuous progress, erecting hundreds of structural bays in parallel operations. Inside, the factory's layout followed a vertically integrated production flow. Raw materials entered at one end and passed through successive stages of battery cell fabrication, module assembly, and finally powertrain integration. To support this, the building's design included wide-span bays and a column-free floor plan for maximum flexibility. Utility corridors were embedded both overhead and beneath the slab to house compressed air, process water, chilled water lines, and high-voltage electrical conduits. HVAC systems were configured to manage precise temperature and humidity tolerances essential for lithium-ion battery production. In terms of energy use, the building was engineered to eventually operate on renewable sources. Roofing was structured to support photovoltaic panels, and internal systems were optimized for energy recovery and minimal waste. Fire suppression posed unique challenges due to the chemical nature of the materials. Thus, specialized foam systems and compartmentalized fire zones were integrated into the design. Construction logistics had to accommodate a remote site with limited access roads. Materials were staged off-site and trucked in with just-in-time precision to minimize storage on the congested site. Labor coordination was also a challenge, requiring thousands of workers from multiple trades and subcontractors, all operating under tight schedules and strict safety protocols. By scaling battery production to such a degree, Gigafactory Nevada marked a shift in how energy storage systems could be manufactured, economically, locally, and with the intent of creating a closed-loop supply chain.
From the outset, the Mac Innovation Park in Scottsdale presented a high-performance build scenario shaped by advanced logistics, rapid vertical development, and site-specific architectural programming. Situated within a high-demand commercial corridor, the project required precision scheduling and a phased construction approach to erect multiple speculative and build-to-suit structures tailored for high-tech manufacturing, office, and research uses. The first major activity involved grading and compaction over a multi-acre footprint. Scottsdale's desert soil conditions demanded moisture conditioning, followed by repeated passes of sheepsfoot and smooth drum rollers, monitored continuously with nuclear density testing to confirm subgrade integrity. Stormwater retention and drainage systems were integrated early, using a combination of underground retention vaults and surface bioswales lined with riprap to mitigate flash flood risks typical of monsoon seasons. Civil crews trenched for extensive underground utilities, embedding large diameter conduits and reinforced concrete storm drains well before foundations were poured. Structural systems across the park consisted primarily of tilt-up concrete panels, a method selected for its speed, cost efficiency, and thermal mass benefits in a desert climate. Once formwork was set on large slab beds, each wall panel was cast with embedded window bucks, utility sleeves, and conduit stubs. Steel reinforcement was tied with exacting placement to meet seismic and wind load criteria. After curing, these panels were lifted using high-capacity hydraulic cranes and braced temporarily with diagonal steel supports until the roof structure was completed. The concrete mix design included admixtures for shrinkage control and compressive strength exceeding 5,000 pounds per square inch to allow for early panel lifting without compromising durability. Roof structures utilized open-web steel joists supported by steel girders and columns anchored to footings with precision-aligned base plates and epoxy-grouted anchor bolts. Decking was installed using high-shear connectors and puddle welds, then covered with insulation and a reflective TPO membrane for energy efficiency. HVAC systems were rooftop-mounted and supported by custom-built steel dunnage frames to reduce structural penetration through the roof. Mechanical coordination involved extensive pre-planning through building information modeling to avoid clashes between ductwork, piping, and electrical raceways within tight ceiling plenum spaces. Interior build-outs were varied depending on the end user, but commonly involved raised access flooring, modular cleanroom compatible partitions, electrostatic discharge safe surfaces, and filtered ventilation systems for research or manufacturing spaces. Electrical infrastructure featured heavy capacity switchgear, isolated ground panels, and redundant feeds where mission-critical operations were anticipated. Fiber optic cabling and wireless mesh networks were embedded throughout to support high data throughput and low latency connectivity. The exterior envelope included architectural elements such as aluminum curtain walls, insulated metal panels, and sunshade louvers oriented according to solar exposure analysis. Landscaping featured xeriscape planting schemes with drip irrigation systems and shaded pedestrian pathways to enhance sustainability and user comfort. Site lighting was designed with cut-off optics and smart sensors to minimize light pollution while ensuring safety.
Starting from its immense foundation work, the construction of Panorama Tower in Miami was an engineering endeavor that pushed the limits of vertical urban development in South Florida. The site preparation required the excavation of a deep foundation mat nearly 10 feet thick, which would ultimately support the enormous structural loads of what became the tallest building in the state. The tower's foundation system relied on a network of auger cast piles extending more than 100 feet below grade, drilled through soft coastal sediments into underlying limestone strata. A high-strength concrete pour of over 13,000 cubic yards was executed in a continuous operation lasting more than 24 hours, involving dozens of concrete trucks in a carefully choreographed rotation. Once vertical construction began, the superstructure rose rapidly using a cast-in-place concrete core system. The central shear walls formed the backbone of the tower, housing elevator shafts, stairwells, and mechanical risers. Surrounding this core, post-tensioned concrete slabs and columns were poured in a cycle of roughly one floor every 4 to 5 days. To maintain this pace, formwork systems were mounted on self-climbing hydraulic jacks, and a just-in-time delivery system kept materials flowing without congesting the tight urban staging area. The building's mix of residential, commercial, and hotel uses demanded varied floor layouts and load-bearing considerations. Transfer girders, some spanning over 30 feet, were integrated at podium levels to redistribute structural loads around open lobby and amenity spaces. These massive concrete beams required temporary shoring towers and custom formwork assemblies, built and dismantled as the structure progressed upward. Mechanical systems throughout the tower had to account for vertical reach, energy efficiency, and hurricane resilience. Multiple chiller plants were stacked vertically at mechanical floors to optimize thermal load distribution. Water pressure zones were engineered using variable speed booster pump systems and brake tanks to maintain consistent pressure throughout the more than 80 stories. The electrical system incorporated dual feeds and emergency backup generation housed on elevated floors to avoid flooding risk. Vertical duct shafts were carefully coordinated with structural elements using 3D modeling tools to prevent clashes. The curtain wall system was engineered for high impact resistance and thermal performance. Each panel included laminated glass, extruded aluminum frames with thermal brakes, and anchoring systems rated for over 170 miles per hour wind loads. Installation occurred using mast climbers and swing stages, starting from the mid-tower levels and working both upward and downward. Balconies were constructed with cantilevered concrete slabs and glass railings carefully sloped to direct water runoff away from the facade. Elevator logistics were especially critical in such a tall structure. High-speed gearless traction elevators with destination dispatch were installed to minimize wait times, and reinforced machine rooms were positioned at intervals to house motors and control equipment. Fire protection systems included pressurized stairwells, zoned sprinkler systems, and smoke control fans, all tied into a centralized life safety command center.
The O'Hare 21 terminal expansion is a transformative aviation infrastructure program designed to reimagine Chicago O'Hare International Airport for the demands of 21st century air travel. At the heart of the program is the replacement and expansion of Terminal 2 with a new global terminal, along with the construction of 2 new satellite concourses and extensive modernization of existing terminal facilities. This multi-billion-dollar initiative involves complex phasing, advanced construction techniques, and tight coordination with airport operations to ensure uninterrupted service throughout the project's delivery. Site preparation began with the demolition of ancillary buildings, relocation of utilities, and reconfiguration of aircraft taxiways and service roads surrounding Terminal 2. Given the proximity to active runways and operational terminals, safety and logistics planning were paramount. Construction staging areas were established on airside and landside zones, complete with dust control systems, lighting, fencing, and noise monitoring. Crews implemented an array of protective measures to shield live taxiways, including jet blast deflectors, reinforced barriers, and safety exclusion zones. The replacement of Terminal 2 with the new O'Hare Global Terminals required complex foundational engineering to support a significantly larger and more structurally ambitious building. The substructure design utilized a grid of deep foundations composed of drilled shafts extending into glacial till and bedrock, with pile caps and grade beams forming the structural base. The mat foundation was poured in large segments with high-strength concrete using thermal control techniques to manage the heat of hydration and ensure structural integrity. The global terminal's superstructure consists of long-span steel framing, using massive plate girders and trusses to create column-free interior spaces for check-in, security, and baggage handling areas. The design required the prefabrication of structural steel assemblies off-site and timed delivery for erection using tower cranes and mobile lifting equipment. Steel members were connected using high-strength bolts and full penetration welds, with temporary bracing to stabilize the frame until the diaphragm action of the floor slabs was established. Curved roof geometry and soaring ceiling heights define the architectural vision for the terminal. The roof system uses a series of structural arches and purlins supporting metal decking and multiple layers of insulation, waterproofing, and reflective membrane roofing. Skylight assemblies, suspended from trusses, bring daylight into the terminal's core and were installed using swing stages and engineered rigging plans. The 2 satellite concourses are connected to the global terminal via underground pedestrian tunnels, constructed using cut-and-cover techniques and temporary earth retention systems. These tunnels house moving walkways, mechanical and electrical systems, and emergency egress paths. Utility corridors beneath the tunnels carry chilled water, fire suppression, data cables, and potable water piping from the central utility plant to each concourse. Terminal interiors are being built with modular construction techniques to allow rapid deployment and future flexibility. Raised access flooring systems provide underfloor distribution for power, data, and HVAC, supporting quick tenant turnover and reconfiguration. High-performance glazing systems are installed on the terminal facades to improve thermal comfort and reduce energy loads. These systems feature low emissivity coatings, thermally broken aluminum frames, and automated sunshades responsive to solar orientation. Mechanical, electrical, and plumbing systems are integrated into the terminal's core and distributed across vertical and horizontal chases. The HVAC design includes dedicated outside air systems with energy recovery ventilators, variable air volume units, and high-efficiency chillers linked to a central plant. The electrical backbone includes redundant switchgear, generator backup, and uninterruptible power supply units for critical systems such as flight information displays, security, and baggage handling. The baggage handling system spans the new global terminal and the satellite concourses, incorporating inline explosive detection screening, high-speed conveyors, and smart routing software. The system is built within a multi-level service zone and coordinated in detail using building information modeling to avoid clashes with structural and mechanical elements. Tilt tray sorters and destination-coded vehicle systems ensure rapid and accurate baggage movement across large distances. Airside infrastructure includes new aircraft gates with dual jet bridges, apron repaving, and reconfigured taxi lanes. Jet fuel hydrant lines are installed below the apron, connected to the airport's fuel farm via loop distribution mains. Each gate is equipped with ground power units, preconditioned air, and visual docking guidance systems, integrated into a digital apron management system that coordinates aircraft movements and turnaround operations. Passenger experience enhancements include expanded security screening zones with automated screening lanes, centralized customs and immigration processing, and intuitive wayfinding systems. Vertical circulation is handled through panoramic elevators, escalators, and stairs connecting multiple terminal levels. Concession and retail zones are constructed with pre-engineered kiosk platforms and coordinated MEP stubs, allowing rapid fit-out and tenant flexibility. Throughout construction, phasing and operational continuity are managed using detailed sequencing plans, temporary passenger corridors, and modular temporary facilities. Security zones are maintained with physical barriers, credentialed access, and 24/7 surveillance. All work must comply with Federal Aviation Administration regulations and be coordinated with the Transportation Security Administration and Air Traffic Control.
One of the most logistically demanding elements of the Las Vegas Convention Center expansion was its integration with an active facility that could not afford operational downtime. The construction team had to carefully phase demolition, excavation, and vertical build-out around major events and conventions, often working night shifts and off hours to avoid disruptions. The expansion project added more than 1 million square feet of new space, including exhibit halls, meeting rooms, and circulation areas, requiring a steel and concrete structural system capable of spanning large, column-free zones. The foundation work began with deep excavation and pile driving. Given the loose alluvial soils common in the Las Vegas Valley, crews installed hundreds of auger-cast piles, each reinforced with steel cages and Tremie-poured concrete. A thick mat slab was then poured over this foundation grid, embedded with conduits for electrical distribution and floor drainage systems. The use of high-strength concrete mixes with specific slump tolerances ensured uniform performance and reduced cracking across the massive floor plate. The superstructure utilized a composite framing system combining wide-flange steel beams and concrete floor decks cast over metal decking. This method provided both strength and speed, allowing trades to follow closely behind the steel erection teams. Tower cranes and mobile telescopic cranes hoisted beam segments and roof trusses into place. For the convention hall roofs, long-span trusses were assembled in staging yards and lifted in modular sections to minimize on-site welding and alignment complexity. Mechanical, electrical, and plumbing systems were designed with scalability and adaptability in mind. Overhead utility zones carried air handling units, fire suppression mains, and lighting circuits along open web joists. These zones were isolated for sound attenuation, using acoustic baffles and vibration isolators to prevent mechanical noise from disrupting presentations and exhibits. Air distribution was handled through a combination of high-volume diffusers and underfloor displacement systems, ensuring comfort across densely populated exhibit spaces. The facade was clad in curtain wall glazing, aluminum composite panels, and architectural fins designed to reduce solar heat gain while delivering a visually striking presence along the strip. Exterior systems were tested for wind and water penetration using mock-up assemblies before full-scale deployment. The entire expansion was tied into a building automation system, enabling real-time monitoring of energy use, HVAC status, and life safety systems across both new and existing facilities.
Bringing TSMC Fab 21 to life in North Phoenix demanded one of the most technically advanced semiconductor facility builds in the United States. This megaproject required a fusion of high-precision cleanroom construction, utility-heavy support infrastructure, and robust seismic and environmental engineering solutions, all executed on a tight timeline within a desert environment. The development began with mass grading across hundreds of acres to establish a stable platform for both the fab itself and the sprawling central utility building, administration spaces, and logistics hubs. Earth-moving operations required both over-excavation and recompaction to meet rigorous load-bearing criteria, particularly for the cleanroom slab, which must maintain a virtually zero tolerance for differential settlement. Vibration mitigation began at the soil level, where layered sub-base configurations and damping materials were installed to reduce micro-vibrations that could interfere with nanometer-scale lithography. Foundation work incorporated a network of heavily reinforced mat slabs and pile caps. In certain zones, deep foundations were installed using auger cast piles to transfer loads well below any compressible strata. The main fab structure was built using steel moment frames and composite metal deck slabs, designed to support not only the cleanroom above, but also extensive overhead mechanical and process utilities routed through a heavily loaded interstitial floor. Cleanroom construction demanded extreme precision. Raised access flooring allowed for laminar airflow, while walls and ceilings were clad in non-shedding, chemically resistant materials. Every seam, panel joint, and utility penetration was sealed to ISO standards, with HEPA filter housings integrated into a grid of fan filter units in the ceiling plenum. Environmental conditions, temperature, humidity, and airborne particle count had to remain within ultra-narrow tolerances, requiring redundant HVAC systems, deionized water production units, and high-efficiency gas scrubbers. The scale of process utility integration was immense. An underground pipe rack corridor was constructed to distribute ultra-pure water, specialty process gases, slurry lines, vacuum systems, and chemical waste returns. All pipe systems were color-coded and installed with leak detection, double containment, and purge capability. Above-ground utility bridges spanned between the central utility plant and the fab, carrying high-volume, chilled water, nitrogen, and clean dry air lines across multiple levels. The central utility building itself was a complex of power transformers, chillers, boilers, air compressors, and chemical delivery systems. Redundant backup generators and uninterruptible power supplies were installed to ensure zero downtime in critical process areas. High-voltage electrical rooms were isolated with arc flash rated enclosures, while transformers and switchgear were mounted on isolated slabs to prevent mechanical vibration transmission. Environmental compliance drove the inclusion of advanced waste treatment facilities and air emissions controls. Scrubber stacks, flare systems, and liquid neutralization tanks operated around the clock to process both hazardous and non-hazardous waste streams. Permitting required continuous environmental monitoring and real-time reporting capabilities. Security and access control were embedded into the site design. Guardhouses, secure perimeters, and biometric access zones were installed to protect intellectual property and personnel. The internal circulation of materials followed a just-in-time logistics model, supported by automated guided vehicles and robotic systems operating in designated corridors beneath the cleanroom floor.
Amid Florida's subtropical flatlands, the construction of Babcock Ranch Solar Town set out to prove that sustainable urban planning and utility-scale renewable energy could coexist in a master-planned community from the ground up. The project began with a rigorous environmental assessment of over 17,000 acres, ensuring that the development footprint would minimize disruption to existing wetlands and wildlife corridors. Extensive hydrological modeling was undertaken to manage the region's natural water flow patterns, with key areas set aside as conservation zones and integrated into the town's stormwater infrastructure. Once the primary civil grading was complete, roadways, utilities, and fiber optic communication lines were laid in tandem using a trench and backfill system coordinated through GPS-enabled machine guidance. Electrical distribution, unlike in most traditional developments, was built with solar generation as the core, not the supplement. Massive photovoltaic fields were constructed just outside the residential core, spanning hundreds of acres. The solar array used fixed tilt panels mounted on driven steel piles with underground cabling channeling direct current electricity to inverters and step-up transformers before feeding into the regional grid. Residential construction throughout Babcock Ranch adhered to rigorous energy efficiency and wind resilience standards. Homes were built with insulated concrete form walls, impact-rated glazing, radiant barrier roof sheathing, and deep roof overhangs to mitigate solar gain. Roofing materials were chosen for their reflectivity and durability, including metal and tile products designed to exceed hurricane uplift requirements. Mechanical systems included high-SEER HVAC units, advanced dehumidification control, and smart thermostats integrated into home automation networks. What differentiated the town further was the full integration of microgrid technology. Battery storage facilities, housed in climate-controlled steel enclosures, provided grid balancing and backup capabilities. These systems ensured continuous power delivery even during grid disturbances and could island the town if necessary during extreme weather events. Switchgear, transformers, and substations were elevated on reinforced concrete pads with flood-proof enclosures and remote diagnostic sensors to prevent failure during high water levels. Public buildings and amenities, including schools, commercial centers, and community centers, were constructed using a design-build delivery method to ensure consistency in green building standards and rapid delivery. All structures were wired for net metering, demand response control, and energy use feedback systems. Building envelopes featured continuous insulation, reflective membranes, and operable windows for cross-ventilation, where applicable passive cooling elements such as overhangs, louvers, and vegetative shading were incorporated into the architecture. Pedestrian infrastructure was planned ahead of vehicular design, with wide pathways, permeable paver systems, bioswales, and shade structures forming the connective tissue of the community. Stormwater is handled via a series of vegetated retention basins and interconnected canal systems, which serve dual purposes of flood mitigation and habitat support. Water and wastewater treatment systems were decentralized and included reclaim systems for irrigation, with smart meters installed throughout to promote conservation.
The Port of Long Beach Middle Harbor Redevelopment Project is a large-scale maritime infrastructure initiative aimed at modernizing and consolidating two aging shipping terminals into a single, highly automated, and environmentally sustainable container terminal. Located within one of the busiest ports in the United States, the project enhances cargo handling capacity, operational efficiency, and environmental performance, positioning the Port of Long Beach as a global leader in port technology and green logistics. Spanning over 300 acres, the redevelopment required extensive dredging, land reclamation, structural upgrades, and the implementation of advanced terminal automation systems. The initial phase of the project involved the demolition of obsolete structures, including wharves, cranes, warehouse buildings, and paved storage yards. Asbestos abatement, utility disconnection, and hazardous materials removal were carried out before full demolition could proceed. Controlled demolition methods and water suppression systems were used to mitigate dust and environmental impact. Salvageable materials such as steel, concrete, and timber were sorted and recycled, aligning with the port's sustainability goals. Once the site was cleared, major marine construction began. The waterfront area underwent significant dredging to deepen the berths to accommodate post-Panamax and ultra-large container vessels. Dredging operations used hydraulic cutter suction and clamshell dredges, removing silt and sand to reach depths exceeding 50 feet. Dredged materials were transported to offshore disposal sites or used as fill for land reclamation elsewhere within the harbor. The berths were then reconstructed with reinforced concrete wharf structures supported by large-diameter cast-in steel shell piles driven deep into the subsurface sediments. Each wharf section was designed to support the next generation of ship-to-shore gantry cranes, requiring high-capacity pile caps and deck slabs with post-tensioned reinforcement. Fender systems, mooring bollards, and ship access ladders were installed along the quay wall, meeting international standards for vessel accommodation. The cranes themselves were mounted on embedded crane rails with power and data conduits integrated into the wharf edge, enabling fully electrified operation. Simultaneously, the terminal's backland area was regraded and compacted to create a uniform, high-strength surface for container storage, truck lanes, and support facilities. Paving was done using reinforced concrete designed for heavy axle loads. A network of subsurface utilities, including stormwater drains, electrical conduits, water mains, and fire protection loops, was installed below grade, coordinated through 3D modeling to avoid conflicts and streamline future maintenance. One of the hallmark features of the Middle Harbor redevelopment was the integration of automation technology into terminal operations. Automated stacking cranes, guided by a terminal operating system, were deployed in container yards. These cranes operate on fixed rails and are powered by electricity, dramatically reducing emissions and labor costs. Containers are moved between yard stacks and transfer zones, where manned or automated vehicles deliver them to and from ships or trucks. Positioning accuracy, collision avoidance, and task optimization are managed through centralized software, interfacing with container tracking systems and real-time data networks. The truck gate complex was also redesigned to support rapid processing and minimize idling. Optical character recognition, biometric verification, and license plate readers were installed to allow for automated identification and routing. RFID tags on containers and chassis enable seamless integration with the TOS, ensuring drivers are directed efficiently through the terminal. Queue management systems, electronic signage, and automated barriers improve safety and operational flow. The Middle Harbor Terminal was designed with an all-electric infrastructure to reduce its environmental footprint. This included electric cranes, yard tractors, and refrigerated container plug-ins powered by the terminal's shore-based electrical system. Ships docking at the terminal are provided with shore power connections, allowing them to shut down auxiliary engines and eliminate emissions while at berth. Substations and electrical vaults were strategically placed to distribute medium-voltage power throughout the terminal, while redundancy was built in to ensure uptime reliability. Stormwater management was another key environmental component. The redevelopment included construction of biofiltration basins, permeable paving in select areas, and underground detention systems to control runoff. These systems filter pollutants and reduce discharge volume into harbor waters. In addition, lighting systems were upgraded with LED fixtures and dark sky compliant shielding to minimize light pollution and energy consumption. Rail infrastructure was also upgraded to support near-dock intermodal capabilities. New tracks, switches, and crossovers were constructed to tie the terminal into the Alameda Corridor rail network, allowing for the direct transfer of containers between ships and trains without truck drayage. Rail-mounted gantry cranes service the on-dock rail yard, loading and unloading double-stack container trains efficiently while maintaining schedule flexibility. Construction was phased to allow portions of the terminal to come online, while other sections remained under development. Each phase included commissioning and testing of all systems, training of personnel, and calibration of automated equipment. Extensive coordination was maintained with the U.S. Coast Guard, Environmental Protection Agency, and local air quality districts to ensure compliance with safety and environmental regulations.
Breaking ground on the new Las Vegas Stadium project involves an immediate confrontation with both scale and site complexity. Before construction on any vertical elements could begin, civil crews undertook mass grading operations across a site encompassing dozens of acres situated near critical transport infrastructure. Excavation equipment worked around the clock to balance cut and fill volumes, and sediment control basins were installed to comply with regional stormwater regulations. Soil stabilization techniques, including lime treatment and compaction grouting, were applied in zones identified by geotechnical surveys as having potential for settlement. The structural skeleton of the stadium is expected to be a composite of reinforced concrete cores and structural steel framing, optimized to support a multi-tiered seating bowl and a retractable roof or canopy. Temporary shoring towers and formwork systems will be deployed to construct the poured-in-place vertical cores, which will house elevator banks, mechanical risers, and egress stairs. Once the cores reach adequate height, sequential steel erection will begin. This involves the staged installation of primary steel columns, roof trusses, and raker beams, using crawler cranes capable of operating at tight radii due to the constrained urban site. Simultaneously, the substructure below grade will include utility tunnels, equipment vaults, and mechanical rooms. These require waterproofing membranes, concrete admixtures for sulfate resistance, and cast-in-place slab systems with embedded sleeves for mechanical and electrical penetrations. Mechanical engineers will be installing a central chilled water plant, routing large-diameter piping through below-grade trenches and into elevated concourses through a system of vertical shafts and distribution headers. The stadium's envelope will likely employ high-performance glazing, custom aluminum rain screen panels, and photovoltaic-ready roof surfaces. These components will be supported by secondary steel framing and sealed using multiple air and moisture barrier systems. Installation of the facade will proceed from multiple elevations concurrently, using mast climbers and suspended scaffold systems. Wind bracing and lateral load transfer connections will be closely monitored during this phase using field weld inspections and survey control points. Interior fit-out will be driven by overlapping trades working in tiered zones, beginning in back-of-house service corridors and proceeding outward to premium suites, concessions, and seating areas. Audio-visual integration, including massive LED boards, arena-grade speaker systems, and real-time data infrastructure, will require extensive cable tray systems and climate-controlled control rooms. The new Las Vegas Stadium will ultimately stand as a hyper-engineered fusion of sports architecture and logistical orchestration, delivering a landmark capable of hosting international events and enhancing the city's already iconic skyline.
Future. Kicking off the South Central Light Rail extension for Valley Metro meant first confronting the reality of retrofitting a major transit infrastructure into an already dense urban corridor. This extension, spanning approximately 5 miles, follows Central Avenue from downtown Phoenix heading south to Baseline Road. Given the alignment through historic neighborhoods and commercial zones, the early stages demanded a highly coordinated effort in utility relocation. Crews had to excavate carefully to identify existing water, sewer, gas, and telecommunications lines, many of which were legacy systems poorly documented, requiring precise trenching, hydrovac excavation methods, and round-the-clock coordination with utility providers to minimize service disruptions. One of the critical structural components was the construction of the double-track guideway. After grading and subgrade preparation, crews moved into placing the track slab. Reinforced concrete forms were installed with dowel bars precisely spaced for anchoring the rail fasteners. Continuous welded rail sections, transported in long lengths to minimize joints, were hoisted and carefully aligned with string-line precision over elastomeric pads to dampen vibration. Each rail was thermite welded in place, a process involving high-temperature aluminum powder ignition to join rail ends seamlessly. The rail alignment required detailed geodetic surveying at every stage to maintain the horizontal and vertical tolerances essential for high-speed urban transit. Bridge modifications were also necessary, particularly at crossings over the Salt River and other drainage channels. Existing bridge structures were retrofitted with new deck panels and lateral bracing to accommodate the added dynamic load of light rail vehicles. Where new bridges were constructed, pile driving and deep foundation systems were implemented using steel H piles driven to refusal. These supports were capped with pile caps and abutment walls, reinforced with high-yield steel rebar cages, tied and placed according to exacting structural specifications. Stations were spaced at intervals that balanced accessibility with operational efficiency. Each station platform required construction of ADA-compliant ramps, tactile warning surfaces, shelter canopies with integrated solar panels, and conduit routing for fare vending machines, lighting, and security systems. Architectural finishes were selected in collaboration with community stakeholders to reflect local cultural identity while adhering to Valley Metro's design standards. Installation of communication and train control infrastructure ran concurrently, involving duct bank installation beneath the guideway and the placement of signal houses and fiber optic cable splicing points. Overhead, catenary systems were mounted atop tubular steel poles secured in augured concrete foundations. The alignment of the OCS required precise tensioning of contact wires, anchored at strategically placed tensioning devices with counterweights to compensate for thermal expansion and contraction. Traction power substations were spaced to ensure consistent voltage across the alignment, each outfitted with switchgear, transformers, and rectifiers enclosed in precast concrete vaults. Throughout construction, maintenance of traffic posed logistical challenges. Central Avenue, being a major arterial route, necessitated phased lane closures, detour signage, and temporary signal modifications. A traffic control plan was continuously updated in coordination with city departments to manage vehicle, bicycle, and pedestrian flow.
Breaking ground on what is envisioned to become the largest retail and entertainment complex in North America, American Dream Miami is a mega project that combines commercial ambition with vast construction scale. The site, spanning several hundred acres in northwest Miami-Dade County, required extensive groundwork before vertical construction could even be considered. Initial site development involved substantial clearing and grubbing of existing vegetation, followed by the removal of unsuitable soils and replacement with engineered fill. Soil compaction and moisture conditioning were conducted systematically, zone by zone, to meet strict geotechnical specifications given the project's susceptibility to high water tables and the underlying karst limestone. Stormwater management was one of the most critical challenges from the onset. Crews installed a comprehensive drainage network composed of perforated HDPE pipes, catch basins, and retention ponds to control runoff during South Florida's intense rainfall events. Because of the site's proximity to sensitive wetlands, strict environmental controls had to be maintained throughout construction. Silt fences, turbidity barriers, and regular environmental monitoring were deployed to ensure compliance with state and federal mandates. The primary structure of the complex comprises a combination of reinforced concrete and structural steel, chosen based on load distribution needs and span requirements. While concrete forms the foundation mat and shear walls, wide-span areas such as the indoor ski slope, water park enclosure, and retail atriums utilize steel framing with long-span trusses and moment connections. The ski slope, one of the central engineering feats, requires a climate-controlled interior envelope over several hundred feet long, with complex thermal insulation and vapor barrier systems. The structural shell is thermally isolated from the surrounding environment, using insulated metal panels and a controlled HVAC system designed to maintain sub-freezing temperatures in a tropical climate. Mechanical, electrical, and plumbing coordination was a substantial portion of the build process, with extensive BIM modeling used to resolve spatial conflicts in densely packed service corridors. Chilled water systems, electrical bus ducts, and fire sprinkler mains all had to be routed through the superstructure without interfering with visitor circulation, escalator shafts, or themed architecture. Substations and cooling towers were strategically located in peripheral service yards to reduce ambient noise and heat near visitor zones. Specialized foundations were needed in areas designated for amusement rides, where dynamic loads exceeded standard building tolerances. Engineers embedded deep auger cast piles beneath the footings to transfer those loads to stable substrata. Vibration isolation systems and seismic expansion joints were installed at strategic intervals to ensure ride safety and structural resilience. Exterior construction involved a layered system of weather-resistant barriers, rain screen cladding, and themed facades that change appearance depending on the function of each zone. Materials ranged from precast concrete panels to architectural glass and high-pressure laminates. For the water park roof, translucent ETFE panels were chosen to allow natural light while minimizing solar heat gain, thereby enhancing energy efficiency.
The Southeast Connector, officially known as the Southeast Connector Project, is a significant transportation infrastructure initiative located in Reno and Sparks, Nevada. Its purpose is to create a vital arterial roadway linking the southern and eastern regions of the Truckee Meadows area, improving regional connectivity, alleviating congestion, and supporting long-term economic development. The project spans approximately 5.5 miles and crosses environmentally sensitive wetlands, floodplains, and existing utility corridors. Its construction required an integrated engineering approach that accounted for hydrology, geotechnical stability, traffic flow, and environmental stewardship. The first phase of construction began with extensive site clearing and grading across the alignment, which traverses areas of previously undeveloped land, sections of the Truckee Meadows floodplain, and former military installations. To prepare the ground for heavy roadway infrastructure, over-excavation and recompaction were performed in areas with poor soil-bearing capacity. Geotechnical surveys identified zones requiring ground improvement, particularly in the marshy areas surrounding the northern end of the corridor. Ground improvement techniques included surcharging, wick drains, and the use of geotextile reinforced embankments to control settlement and increase subgrade stability. The roadway was built on a raised embankment for much of its length to prevent inundation during flood events and to allow for effective stormwater management. Structural fill material, including engineered gravel and crushed rock, was placed in compacted lifts to construct a stable road base. The roadway section includes multiple travel lanes in each direction, shoulders, bike lanes, and a multi-use path, accommodating both vehicular and non-motorized traffic. Median barriers, traffic signage, and roadway lighting were installed to enhance safety and visibility. One of the defining engineering features of the Southeast Connector is the number of bridges and culverts required to cross watercourses and wetland areas. The most prominent of these is the large bridge over the Truckee River, which required deep foundations using driven steel piles embedded into dense subsurface strata. The superstructure consisted of pre-stressed concrete girders and cast-in-place deck slabs designed to accommodate vehicular loading and seismic activity common to the region. Smaller bridges and box culverts were constructed at wetland crossings to maintain hydrologic continuity and allow for wildlife passage beneath the roadway. A central design consideration was floodplain interaction. The project corridor is situated in a basin that serves as a natural floodplain during extreme weather events. To mitigate flood risk and maintain flood capacity, engineers constructed large stormwater detention basins and conveyance channels adjacent to the roadway. These features are integrated with box culverts and drainage structures designed to manage runoff and attenuate peak flows. Hydraulic modeling was used to design these systems, ensuring that the new infrastructure would not adversely impact downstream properties or ecosystems. Extensive environmental mitigation and habitat preservation measures were integrated throughout the construction. The alignment required the relocation of sensitive species, the restoration of disturbed wetlands, and the preservation of existing vegetation where possible. Wetland mitigation included the excavation and grading of replacement wetland areas, installation of native plant species, and long-term hydrologic monitoring to ensure functional equivalence to the impacted habitat. Erosion control measures such as straw wattles, silt fencing, and temporary detention basins were deployed during construction to prevent sediment discharge into natural waterways. The project also involved the relocation and protection of existing utilities, including water mains, sewer lines, gas lines, fiber optic cables, and power transmission infrastructure. Coordinating these utility adjustments required phased shutdowns and rerouting, which were timed to minimize service disruptions. Underground utility corridors were constructed with reinforced concrete encasement in areas of high traffic loading, and all utility crossings were carefully coordinated with the vertical and horizontal alignment of the new roadway. Intelligent transportation systems infrastructure was incorporated into the design to support future traffic management and monitoring. This includes traffic signal controllers, vehicle detection sensors, overhead variable message signs, and camera systems integrated with the Regional Traffic Operations Center. These technologies allow for real-time traffic updates, incident response coordination, and improved safety for corridor users. Pedestrian and cyclist infrastructure was also prioritized. The entire length of the Southeast Connector includes a separated, paved, multi-use path designed for both recreational and commuter use. Grade-separated crossings and protective barriers enhance safety for non-motorized users. Trailheads with parking, lighting, and informational signage were developed at key access points, encouraging public use and improving community connectivity. Construction sequencing was managed to maintain local access, protect environmentally sensitive areas, and ensure continuous progress through seasonal weather changes. Major earthworks were scheduled for dry months, while bridge and drainage construction proceeded during cooler seasons with controlled dewatering and water quality monitoring. Daily inspections and environmental compliance reporting were conducted to maintain adherence to permits and minimize ecological impacts.
Unlike many arenas that rise from open space, the T-Mobile Arena in Las Vegas was constructed on a tightly constrained urban site, requiring deep logistical planning before the first shovel hit the ground. The initial site preparation involved extensive utility relocation, as existing storm drains, water lines, and power conduits had to be rerouted to accommodate the building footprint and its supporting infrastructure. With minimal laydown space available, construction sequencing was planned in detail to ensure materials arrived just in time for installation. The structural system relied on a hybrid steel and concrete frame. A reinforced concrete core formed the arena's vertical circulation spine and housed elevator shafts, stairwells, and mechanical risers. Around this core, a complex array of steel columns, raker beams, and trusses supported the sweeping roof and cantilevered seating decks. The roof was particularly challenging, as it required long-span trusses to bridge the open interior without intermediate columns, allowing unobstructed views from all seats. These trusses were lifted into place using synchronized crane lifts and were temporarily braced until lateral systems were completed. Within the bowl, precast concrete seating components were craned into position and set atop steel support members. The lower bowl was poured in place using cast-in-place concrete, allowing for integration of conduit chases and drainage systems directly into the slab. To ensure optimal acoustics, the interior envelope was lined with a combination of perforated metal panels and acoustic baffles, carefully arranged to diffuse sound energy and minimize echo. Mechanical systems were installed using vertical and horizontal distribution zones to maximize ceiling clearance and fan comfort. Chilled water plants, air handling units, and ductwork were located primarily above the event floor and distributed outward through high-level plenums. Special attention was given to integrating smoke control zones, emergency exhaust fans, and CO2 sensors into the overall HVAC design. Electrical systems featured redundant feeds, backup generators, and an extensive network of lighting control nodes to accommodate both performance and broadcast demands. The arena's exterior featured a curved facade made up of glass curtain wall, aluminum panels, and exposed structural elements. These were installed in phased sequences, using mast climbers and boom lifts to operate within the spatial limits of the surrounding development. Water infiltration protection was handled using rain screen design and perimeter sealant systems, ensuring long-term envelope integrity in the arid climate.
Unlike traditional airport projects built in undeveloped areas, the Mesa Gateway Airport expansion required surgical precision to retrofit and expand critical infrastructure within an operational airfield. The effort spanned terminal growth, airside improvements, and upgrades to utilities, all orchestrated under strict Federal Aviation Administration compliance and continuous coordination with airport operations. Initial groundwork focused on expanding the commercial terminal. This involved selective demolition of existing structures and pavement, followed by deep trenching to relocate utility lines such as jet fuel piping, communications fiber, and storm drains. Excavation was staged to avoid conflicts with active taxiways and required trench shielding, dewatering pumps, and utility phasing plans that prevented disruption to existing airport services. Potholing and ground-penetrating radar scans were performed to identify undocumented legacy utilities from the site's previous military use. Terminal expansion required a structural system that combined steel moment frames with composite decking, supported by drilled piers tied into deep foundation beams. The steel frame was erected using high-reach cranes that were coordinated with the airport's control tower to avoid airspace intrusion, particularly during girder lifts near the active apron. Roof decking was fireproofed with sprayed-applied materials, and roof insulation assemblies were capped with a single-ply membrane roofing system designed to withstand high desert UV exposure and monsoonal winds. Passenger processing areas were built with forward-looking flexibility. Baggage handling systems were laid out beneath the slab-on-grade level, supported by trench drains and conveyor pits formed with cast-in-place concrete. Conveyor belts, diverters, and scanners were pre-assembled off-site and installed as modules to reduce installation time within a compressed schedule. Check-in counters, TSA security lanes, and automated boarding gate systems were backed by robust data infrastructure routed through overhead cable trays, linked to secure IT closets and network hubs located in protected zones behind the scenes. Airside improvements extended to taxiway extensions and apron reconfiguration. Crews used slip-form paving machines to place Portland cement concrete with dowel joints, constructed in multi-lane widths with tight alignment controls. Concrete batch plant operations had to meet FAA quality standards for airfield pavements, including flexural strength and surface smoothness. New lighting systems, edge lights, taxiway center lines, and approach indicators were installed within pavement cans fed by underground duct banks, all tied into the airport's airfield lighting control system. Jet bridges were added and coordinated with apron regrading to match aircraft door sill heights. Reinforced apron paving with fuel hydrant pits, ground power units, and potable water hookups were integrated at each new gate position, enabling faster turnaround times for commercial airliners. Drainage for apron areas was routed to oil-water separators to maintain environmental compliance before entering the municipal storm system. To support future growth, a new central energy plant was constructed, housing chillers, boilers, backup generators, and water softening systems. Mechanical systems were routed through underground utility corridors leading to terminal mechanical rooms equipped with air handlers, VAV boxes, and HEPA filtration. All critical systems were designed with N+1 redundancy to ensure uninterrupted operation.
With the latest additions to the landscape of modern entertainment engineering, Universal Orlando's Epic Universe stands as a formidable example of how large-scale theme park development pushes the boundaries of construction logistics and immersive design. Conceived as an expansive new addition to the Universal Orlando Resort, the project required the transformation of over 700 acres of previously underutilized land into a fully integrated theme park environment. The initial phases of the project began with comprehensive site surveying, geotechnical analysis, and land clearing. Crews needed to regrade vast swathes of land to ensure proper drainage and structural stability. Underground utilities, including high-capacity stormwater management systems and electrical conduit networks, were laid out early in the process to avoid costly rework during vertical construction. To accommodate the multi-gate layout, civil engineers mapped out internal roads, pedestrian paths, and backstage support corridors, all designed to handle the anticipated heavy volume of guests and service vehicles. A series of massive retention ponds were excavated not just for water management, but also to act as visual and thematic barriers between different park zones. Construction staging areas were carefully allocated at various nodes around the site, enabling multiple trades to work simultaneously on the various themed lands. Structural frameworks for each land within the park varied significantly depending on the thematic and functional requirements. Steel-framed show buildings featuring complex soundproofing and HVAC systems were erected using tower cranes and prefabricated panel systems. Foundations had to be over-engineered in certain zones to support the enormous static and dynamic loads associated with ride systems, many of which rely on high-speed launches, track-switching mechanisms, or deeply embedded hydraulic lifts. In some attractions, such as those simulating flying or space travel, vibration isolation pads were incorporated beneath the concrete slabs to prevent mechanical resonance and structural fatigue. Mechanical integration posed a particular challenge given the density of infrastructure. Each attraction required its own climate control, power supply, data networking, and life safety systems. Fire suppression, especially in dark ride environments, had to meet stringent code requirements while remaining concealed within themed architecture. Likewise, air handling units were often buried underground or hidden in faux architectural elements to preserve the illusion of immersive storytelling. Exterior theming was a collaborative effort between construction teams, scenic artists, and rockwork specialists. Shotcrete sculpting was extensively used to fabricate mountains, castles, and alien landscapes. Fiber-reinforced polymer cladding was applied to facades for lightweight but durable finishes. Paint crews worked alongside sculptors to apply multi-layered coatings that would resist Florida's intense UV exposure and frequent rainfall. A particularly sophisticated aspect of the project involved park-wide integration of a digital experience layer, necessitating deep trenching for fiber optic cabling and distributed antenna systems. This infrastructure underpins everything from mobile app-based ride reservations to location-aware character interactions.
The American Legion Bridge Replacement Project is a critical infrastructure effort aimed at modernizing a key segment of the Capital Beltway. Specifically, the Interstate 495 corridor that spans the Potomac River between Maryland and Virginia. The existing American Legion Bridge, originally constructed in 1962, has long operated over capacity, experiencing severe congestion and structural fatigue due to increasing vehicular loads. The replacement project involves the complete removal of the aging bridge and construction of a new, expanded structure with improved capacity, safety, and multimodal functionality, all executed while maintaining active traffic flow across one of the busiest regional thoroughfares in the Mid-Atlantic. Construction begins with extensive preparatory work on both the Maryland and Virginia approaches. This includes widening the approach roads, relocating utilities, and constructing temporary service roads and retaining walls. Given the high traffic volume, much of this work occurs during off-peak hours with protective barriers and advanced traffic management systems deployed to safeguard workers and minimize disruptions. Intelligent transportation systems, including dynamic signage and real-time traffic monitoring, are established early in the project to maintain safe and efficient operations throughout construction. The new bridge is designed as a multi-span, pre-stressed concrete and steel girder structure with a substantially wider deck than its predecessor. It will accommodate additional general-purpose lanes, managed toll lanes in each direction, full shoulders, and a shared use path for pedestrians and cyclists. To support this expanded deck width, the new substructure includes larger piers and abutments constructed on deep foundations. Drilled shafts and driven steel piles are employed to reach load-bearing rock formations beneath the riverbed, with extensive underwater geotechnical investigations conducted to guide pile placement and sizing. Before the existing bridge can be removed, new bridge elements are constructed parallel to or in segments alongside the current bridge alignment. This phased construction approach minimizes the need for full closures, as traffic can be diverted to temporary bridge sections or shifted onto newly completed portions of the structure. Barges and temporary trestles are used to support materials transport and crane operations on the river, reducing dependency on land-based access and improving construction efficiency in the constrained corridor. The bridge superstructure consists of a composite steel girder and concrete deck system. Long-span steel girders are fabricated off-site, trucked to staging areas, and lifted into position using barge-mounted cranes and land-based crawler cranes. The girders are then spliced and secured using field welding and bolted connections. Once in place, the cast-in-place concrete deck is poured in sections, using form travelers and screeding equipment to ensure uniform thickness and surface smoothness. The deck is reinforced with high-strength steel rebar and includes post-tension tendons for enhanced performance under dynamic traffic loading. Drainage and expansion systems are integral to the bridge's durability. Deck drains, scuppers, and downspouts are installed to direct stormwater into collection systems without discharging directly into the river. Expansion joints and elastomeric bearings accommodate temperature-induced movements and vehicular loading, while corrosion-resistant materials and coatings are specified throughout to withstand de-icing chemicals and riverine humidity. The shared use path, located on the upstream side of the bridge, is physically separated from vehicular traffic and includes safety railings, lighting, and observation points. It connects to regional trail networks on both sides of the Potomac, enhancing non-motorized connectivity between Maryland and Virginia. The path structure is cantilevered from the main deck girders and supported with steel outriggers and braced frames designed for pedestrian loads and vibration criteria. Approach work involves realigning entrance and exit ramps, expanding merge lanes, and upgrading interchanges near the bridge termini. Retaining walls, noise barriers, and landscaping are constructed in tandem with grading and paving operations. Signal systems, gantries for toll lane management, and overhead variable message signs are installed and connected to regional traffic control centers via fiber optic networks embedded in conduit runs along the bridge structure. Environmental protections are implemented throughout the construction process. Silt curtains, turbidity barriers, and erosion control blankets prevent sediment from entering the Potomac River. Construction activities are scheduled to avoid sensitive spawning seasons for aquatic life, and work platforms are equipped with spill containment measures. The project also includes habitat restoration features such as riverbank stabilization and replanting of native vegetation along disturbed shoreline areas. Bridge lighting is designed to minimize glare and light pollution, using LED fixtures with shielded optics. Power and communication conduits are embedded in the deck to serve future upgrades in traffic technology and maintenance monitoring. The bridge is equipped with structural health monitoring sensors embedded in key components to collect data on strain, vibration, and temperature, allowing for predictive maintenance and long-term performance evaluation. Once traffic is fully shifted onto the new bridge, the original American Legion Bridge is dismantled in sections. This demolition process is executed using a combination of wire sawing, controlled explosive charges for superstructure removal, and mechanical dismantling. Steel girders and concrete components are removed by barge and processed off-site for recycling and reuse.
At the outset of the MSG Sphere's construction in Las Vegas, the most immediate challenge was establishing a foundation capable of supporting a structure unlike anything previously built. The sphere's extreme diameter, spanning over 500 feet, and height exceeding 300 feet, necessitated a ring of deep foundation caissons. These caissons, drilled dozens of feet into the caliche-laden desert subsoil, provided load-bearing support for the concrete mat foundation that would carry the entire dome. Crews installed dense rebar cages and tremi-poured concrete in segments, ensuring continuous integrity under the enormous compressive and lateral loads. The frame of the sphere was formed using a hybrid structural system combining concrete cores with an extensive steel diagrid shell. The steel members, many of them curved and custom fabricated, were craned into place with extreme precision. Each joint had to accommodate subtle geometric variances in the spherical curvature, requiring extensive use of laser surveying and point cloud modeling during assembly. The use of node connectors, each one custom engineered, allowed thousands of steel segments to interlock into a stable geodesic structure. Work progressed concentrically, rising from the base upwards, forming a self-supporting lattice that grew in stages toward closure at the apex. Internally, the complexity intensified. The sphere's defining feature, its fully immersive LED display surface, required a compound curved interior supported by catwalks and rigging systems hidden behind the paneling. This interior surface included more than 100,000 square feet of high-resolution LED panels. Engineers had to account for thermal expansion, cable routing, and precise angles of incidence for projection mapping and acoustics. To achieve truly immersive sound, an advanced beam-forming audio system was suspended behind acoustic mesh panels, calibrated to direct audio precisely to each seat using an array of over 100,000 speakers and transducers. Externally, the sphere's envelope was sheathed in an exoskeleton clad with LED modules designed for all-weather performance. These panels were mounted using modular aluminum frames anchored directly to the diagrid steel. Wind loading, thermal cycling, and desert dust all influenced the choice of materials and mounting systems. Throughout the build, access was achieved with a mix of suspended scaffolds, articulating lifts, and perimeter ring cranes. Construction sequencing had to account for limited laydown space and active coordination with surrounding infrastructure. With the Las Vegas Strip nearby, noise restrictions, traffic control, and night work all shaped how the project advanced. The MSG Sphere stands as a demonstration of digital architecture converging with structural audacity, where immersive entertainment dictated the blueprint from foundation to facade.
The Springfield Rail Improvements Project is a comprehensive transportation infrastructure initiative designed to enhance rail operations, vehicular traffic flow, and safety within the city of Springfield, Illinois. Located along the primary north-south corridor for freight and passenger rail in central Illinois, this project addresses long-standing issues related to at-grade crossings, traffic delays, emergency vehicle access, and community connectivity. It involves the realignment of rail lines, construction of new underpasses and overpasses, installation of modern signaling systems, and the development of consolidated corridors to better manage the coexistence of rail in urban environments. The core of the project is the consolidation of multiple existing rail corridors onto a single, upgraded alignment along the 10th Street corridor, which will serve as the main north-south route for both freight and Amtrak passenger trains. This realignment requires the relocation of tracks previously running along the 3rd Street corridor. As part of this shift, new double-track sections are constructed using continuously welded rail on concrete ties, supported by engineered ballast and subballast layers. Subgrade preparation involved excavation to remove unstable soil, replacement with select fill, and compaction to achieve the necessary bearing capacity and drainage properties. The new corridor includes improvements to the track profile, geometry, and elevation to ensure compliance with modern rail standards. Geometric design ensures proper curve radii, super elevation, and grade transitions, accommodating both high-speed passenger operations and heavy freight trains. Drainage systems, including French drains, culverts, and swales, are installed along the right-of-way to protect the track structure and minimize water infiltration. Grade separation is one of the project's defining features. Multiple new underpasses and overpasses are constructed to eliminate at-grade crossings, enhancing both safety and efficiency. These structures include roadway underpasses with retaining walls, bridge decks, and approach embankments. For underpasses, construction begins with temporary traffic rerouting, followed by excavation and the installation of shoring systems such as sheet piling or soldier pile and lagging walls. Reinforced concrete box culverts or beam and slab bridge decks are installed to carry rail lines over the depressed roadways. Bridge abutments are supported by deep foundations, typically drilled shafts or driven piles, depending on subsurface conditions. Concrete formwork, reinforcement, and pour sequencing are closely coordinated to maintain quality control and structural integrity. Stormwater detention basins and pump stations are added near underpasses to manage runoff and prevent flooding during storm events. Signal and communications infrastructure throughout the corridor is upgraded to include positive train control, wayside signals, automatic block signals, and grade crossing protection where crossings remain. Fiber optic cables are laid in conduits adjacent to the track structure, forming the backbone of the communication system. Signal houses are prefabricated and equipped with relay logic, batteries, and interface panels, enabling centralized traffic control and real-time monitoring of train movements. To minimize disruption during construction, much of the work is staged. Temporary shoe-fly tracks are built to divert rail traffic around active work zones. These detour tracks are constructed to full structural standards and include turnout switches, ballast, and signal integration to maintain continuity of operations. As permanent infrastructure is completed, trains are shifted onto the new alignment, allowing for the removal of old track and crossings. Environmental considerations are integrated into every phase of the project. Wetlands, drainageways, and wildlife habitats are assessed during design, with mitigation strategies implemented where impacts are unavoidable. Erosion control measures such as silt fencing, seeded slopes, and temporary sediment basins are deployed during earthwork operations. Noise and vibration studies are conducted, leading to the installation of sound walls and the use of ballast mats or resilient rail fasteners near sensitive receptors like residential neighborhoods or historic districts. Public engagement is also a central component, with ongoing coordination between city officials, the Illinois Department of Transportation, and the Federal Railroad Administration. Stakeholder meetings, community briefings, and property owner consultations ensure transparency and allow concerns about property access, construction impacts, and aesthetics to be addressed proactively. In many locations, enhancements to urban design are incorporated into the project, including landscaping, pedestrian pathways, lighting, and public art installations that reflect Springfield's cultural identity. The Springfield Rail Improvements Project also supports broader goals of regional transportation planning. By consolidating rail operations onto a dedicated corridor, the project lays the groundwork for expanded passenger rail service, including future high-speed rail connections along the Chicago to St. Louis corridor. It also facilitates improved freight logistics by reducing delays caused by vehicle-rail conflicts and allowing for higher throughput along a modernized rail line. Construction logistics are tightly managed, with detailed scheduling, traffic control plans, and safety protocols. Equipment staging areas, material stockpiles, and worker access routes are established to reduce interference with local traffic and maintain construction productivity. Work progresses in multiple segments simultaneously, leveraging different contractors and crews to meet project milestones while keeping disruption to the community at a minimum.
In the vast and rugged terrain of western Nevada, the Greenlink West Transmission Line project began with a series of extensive environmental and geotechnical surveys. This corridor, stretching hundreds of miles, demanded careful route selection to avoid sensitive habitats, archaeological sites, and unstable soil zones. Once the alignment was finalized, crews mobilized with access road grading as the first priority. In remote desert areas, temporary haul roads and helicopter pads were established to enable movement of personnel, equipment, and materials to tower sites that had no existing access. Tower foundations varied depending on soil conditions. In rocky upland zones, foundation crews used blast hole drilling, followed by concrete anchors set deep into fractured bedrock. In softer or sandy valley floors, deep bored shaft foundations were poured with reinforced concrete, sometimes with steel casing to prevent wall collapse. Each foundation was designed to handle both axial and lateral loads imposed by conductor tension and wind shear on the towers. Concrete had to be batched locally or transported in rotating mixers across significant distances, requiring careful coordination to ensure consistency and curing integrity. The transmission towers themselves were largely lattice steel structures, fabricated off-site and delivered in sectional bundles. Erection crews used tracked cranes where terrain allowed, while in the steepest sections, helicopters were employed to lift tower segments into place. Ground crews then bolted the segments together using high-strength structural fasteners. Each tower was surveyed post-erection for verticality and alignment, using laser theodolites before conductor stringing began. Conductor installation involved multiple phases. First, pilot lines were pulled between towers using drones or helicopters. These were then used to draw in heavier steel messenger cables, which in turn pulled in the high-voltage conductor bundles. Each conductor was tensioned using hydraulic pullers and tensioners to exact sag tolerances specified in the design documents. Spacer dampers were installed at calculated intervals to prevent aeolian vibration, and insulators, often made from composite polymer materials, were mounted to separate the live conductors from the grounded towers. Substations on either end of the line required massive transformers, circuit breakers, and control systems to manage voltage conversion and grid integration. These substations were built concurrently, with site grading, pad installation, and bus work assembly proceeding, while the main line was being erected. The Greenlink West project not only involved transmission infrastructure, but also included communications fiber installation and SCADA integration for remote monitoring, forming a backbone for a more resilient and renewable-focused power grid across the region.
The expansion of the Tesla Gigafactory in Austin, Texas, officially known as Giga Texas, represents one of the largest and most advanced industrial construction efforts in the United States. Located along the Colorado River on the eastern edge of Austin, the site spans over 2,000 acres and serves as a central hub for Tesla's vehicle manufacturing, battery production, and future operations related to its energy and robotics divisions. The expansion of this facility has required large-scale site development, precision engineering, and massive logistical coordination to accommodate the simultaneous construction of multiple production lines and infrastructure systems. Site work began with extensive earth-moving operations to level the vast tract of land and prepare it for heavy industrial use. Bulldozers, scrapers, and excavators were used to move millions of cubic yards of soil, creating a flat and stable platform for foundations. Drainage swales, detention ponds, and underground stormwater systems were installed early in the process to manage runoff and prevent flooding, especially given the site's proximity to the river and its location within a region subject to periodic heavy rainfall. Foundation work for the expanded areas of the Gigafactory involved deep excavation and the construction of reinforced concrete footings, grade beams, and mats, due to the sheer size and weight of the industrial equipment housed within the plant, including stamping presses, casting machines, and robotic assembly lines. Foundations were engineered to extremely tight tolerances. Concrete was poured in large, continuous placements using high-performance mixes designed for strength and durability. Reinforcing steel cages were pre-tied on-site and lifted into place using tower cranes, ensuring consistency and efficiency in the foundation builds. The superstructure of the Gigafactory expansion primarily consists of a steel frame system with large-span girders and open-web joists designed to create wide, column-free interior spaces. This framing approach allows for maximum flexibility in arranging production lines and material handling systems. Structural steel components were fabricated off-site and delivered in sequenced loads for immediate erection. Multiple cranes operated in parallel to lift and set beams, columns, and roof trusses, with crews bolting and welding connections at a rapid pace to maintain schedule. Roof and wall systems are built with insulated metal panels and reinforced concrete tilt-up walls. The use of tilt-up construction provided a quick and durable solution for enclosing the facility. Panels were cast on site in horizontal beds, then lifted into place using specialized rigs and temporarily braced until tied into the structural steel frame. The exterior envelope includes large format glazing, roll-up industrial doors, louvers for mechanical ventilation, and embedded systems for future photovoltaic arrays. Internally, the facility is divided into multiple production zones, including body in white, paint, drive unit, battery cell, and final assembly areas. Each zone is outfitted with an integrated mechanical, electrical, and plumbing backbone tailored to the specific requirements of the manufacturing process. Electrical substations, bus ducts, and motor control centers distribute power to equipment, while compressed air, chilled water, and process piping systems run throughout the structure in overhead utility racks. HVAC systems consist of large rooftop air handling units with variable air volume controls and ductwork engineered for high-volume ventilation. Battery and paint shop areas are served by specialized air filtration systems and climate control to maintain environmental conditions necessary for quality control and safety. Fire protection includes wet pipe sprinkler systems, foam suppression in high-risk areas, and a network of fire alarm panels and detection devices distributed through ceiling and wall cavities. One of the most critical components of the expansion is the battery cell manufacturing area. This section requires ultra-clean environments, achieved through the use of clean room standards and enclosed spaces, positive pressurization, and air filtration. Mechanical isolation, anti-vibration pads, and precision leveling are incorporated into the floor systems to support sensitive equipment like electrode coating machines and cell assembly stations. Material movement throughout the Gigafactory is supported by automated guided vehicles, overhead cranes, and floor-mounted conveyors. These systems are designed to move components and finished products between zones without interfering with human workflow. Logistics tunnels, high bay racking systems, and buffer storage areas are constructed to support just-in-time delivery and reduce operational bottlenecks. The facility's expansion also includes workforce amenities such as office space, cafeterias, training rooms, locker facilities, and employee parking. These support structures are built using conventional steel framing and modular interior finishes. Elevated walkways and observation decks allow management and visitors to safely monitor operations while minimizing interference with production. On the exterior, the expansion incorporates new access roads, loading docks, and utility corridors. Heavy-duty concrete pavements are laid for truck traffic and equipment transport, while perimeter fencing, lighting, and security systems are installed to maintain site safety. Landscape buffers and erosion control measures are implemented to minimize environmental impact and comply with regulatory requirements. The Gigafactory expansion is managed using advanced construction technologies, including building information modeling, 4D scheduling, and real-time project tracking. Construction crews work in multiple shifts to maintain continuous progress, with prefabrication and modular construction methods employed to accelerate timelines.
perched high above the Colorado River, the construction of the Mike O'Callahan-Pat Tillman Memorial Bridge required a level of structural precision and environmental coordination seldom encountered in highway infrastructure projects. Spanning nearly 900 feet across the Black Canyon, just downstream of the Hoover Dam, the project's location presented formidable challenges, including extreme elevation, rugged topography, high winds, and protected surroundings. The goal was to reroute U.S. Route 93 traffic off the Hoover Dam, necessitating a bypass bridge that could support heavy truckloads while enduring significant thermal and seismic forces. Foundation work began with the construction of vertical columns anchored into the canyon walls. These columns required deep rock sockets drilled into the solid bedrock on both the Nevada and Arizona sides. Blasting, rock bolting, and controlled excavation were used to establish working platforms and construct reinforced concrete footings. Once the columns were complete, temporary cable stays were strung across the canyon to support the next phase, the twin-rib concrete arch that would ultimately carry the bridge deck. This twin arch was built using a cantilever segmental method. Crews cast concrete segments outward from each canyon wall in balanced pairs, inching their way across the gap with the aid of a cable-supported highline system and traveling formwork. As each segment cured, post-tensioning tendons were tensioned internally to bind the structure and prevent shear or flexural failure. Each section was surveyed and adjusted using hydraulic jacks to maintain precise alignment as the arch legs advanced toward mid-span. Upon closure of the arch, deck construction commenced. Steel girders were lifted by cranes stationed on temporary towers and connected to the arch ribs through vertical spandrel columns. The bridge deck itself was a cast-in-place concrete slab, poured in sections with embedded rebar and expansion joints to accommodate thermal movement. Barrier rails, lighting systems, and crash protection were then installed along the deck edges. Wind and seismic design were paramount. The bridge incorporates tuned mass dampers and elastomeric bearings at key support points, allowing it to flex under dynamic loading without structural compromise. To ensure safety during construction, catwalks and harness points were anchored throughout the span, and workers operated under a highly regimented fall protection protocol.